welcome to Panimalal Engineering College, where academic excellence meets boundless opportunity. Panimalal Engineering College, an autonomous institution, is a higher educational institution located in Chennai, the hub of the city. This prestigious institution was established in the year 2000 with 180 students and 3 departments: CSE, IT and EC. Founded with a vision to nurture the next generation of leaders and innovators, Panimalal Engineering College is a vibrant community where dreams take flight and aspirations find wings. Total area of the college is 75.43 acres. For 2 consecutive years, Swachh Bharat 2018 and 2019, Panimalal Engineering College has been recognized as Green Clean Campus, a distinction that speaks volumes about our dedication in creating a sustainable and eco-friendly environment. Eight undergraduate courses spanning diverse fields: computer science, electronics and communication, electrical and electronics, artificial intelligence and data science, artificial intelligence and machine learning, information technology, mechanical engineering, science and business system are offered to our students to embark a tailored journey to their passion and aspiration. Panimalal Engineering College offers 3 dynamic postgraduate courses in the field such as ME in Computer Science and Engineering, Communication System and Master of Business Administration, providing advanced education and specialized training. All the eligible courses has been accredited since 2006, supporting student success with modern infrastructure. Our institution provides the students with state-of-the-art facilities to foster their academic growth and practical learning experiences. All the classrooms are constructed in such a way that they are neat and clean with proper lighting and ventilation. These renowned classrooms are equipped with sophisticated smart boards to intensify learning and teaching experiences. The Humanities and Science Department of Panimalal Engineering College plays a crucial
Satish sir.
Yes, ma'am. Ma'am had also joined them.
Okay. Can start it. Yes.
We can start now. Simple, sir. Is there, sir? Shall we start? Simple, sir.
Sir, yes, sir. Yes, sir. I joined, sir.
Yeah, thank you so much, sir. Thank you, sir. Just to confirm, sir. Balaji, sir, are you ready?
Yes, sir. Yes, sir.
So, good evening, everyone joined here. It gives me immense pleasure to welcome you all to the inauguration of the AICTE Atal FDP program scheduled from 1st December to 6th December 2025 on the theme Quantum Intelligence, AI, Quantum Convergence in Cyber Defense and Space Technologies. This FDP is organized by Department of Computer Science and Engineering, Panimalal Engineering College. On behalf of the institution, I extend a warm and respectful welcome to our esteemed management chief patron, Dr. P. Chinnadurai, Secretary and Correspondent of Panimalal Group of Institutions, patrons, Dr. C. Shakti Kumar, Director, Panimalal Group of Institution, Mr. C. Vijay Rajeshwari, Director, Panimalal Group of Institution, Dr. Charanya Shakti Kumar, Director, Panimalal Group of Institution, co-patron, Dr. K. Mani, Principal, Panimalar Engineering College, Dr. S. Prasanna Devi, Chief Academic Officer, Panimalar Engineering College, HOD, Dr. L. Jabashila, and other faculty members of our department. We sincerely thank them for their support, leadership, and continuous encouragement in hosting this 6-day faculty development program. I'm delighted to welcome all participants join us from various colleges, universities, and institutions across India. Your presence reflects your commitment to learning and exploring the rapidly evolving domains of artificial intelligence and quantum technologies. This 6 days faculty development program from 1st to 6th December 2025 aims to provide participants with both foundation and advanced insights in the convergence of AI and quantum computing, an area that is transforming many critical sectors like quantum enhanced AI cyber defense system, secure communication through quantum cryptography, application in satellite data processing and space technologies, advanced quantum algorithms for real-time decision making, quantum machine learning for next generation computing intelligence. This convergence is not just futuristic, it's becoming a national priority for innovation, security, and technological leaderships. With these words, I'm honored to invite our principal, Dr. K. Mani, to welcome the participants of AICT Atal Faculty Development Program on Quantum Intelligence. Mani sir,
சார் பிரின்சிபல் சார் இருக்காரு
principal sir.
சார் இருக்காரு லைன்ல இருக்கார் சார் ப்ளீஸ் வந்தாங்க.
Okay. Next, I invite sir, Mani sir, principal sir.
சார் பிரின்சிபல் சார்
I think the side it is.
நெட்வொர்க்
Not
இஷ்யூ
only-
நினைக்கிறேன் அவர்
Network
இமேஜ்
issue
அப்படி
இருக்குது.
ஸ்டாப்
Yes, some
எஸ்
network
எஸ்
issues.
எஸ்
Yes,
எஸ்
yes,
எஸ்
sir, I would like to invite Dr. Prasanna Devi, Dr. S. Prasanna Devi, Chief Academic Officer, to welcome the gathering and deliver the keynote address.
Good evening to one and all present here. So it's my very happy occasion to invite you all for this Atal FTP. So first of all, I would like to welcome the distinguished resource person, the faculty members present here, the participants, the research scholars, PG scholars, and most importantly, the organizing team, the CSC department. And it really gives me a very happy moment and a pleasure to welcome all the AICT Atal FDP participants. And the title, as Dr. Satish has mentioned, it is Quantum Intelligence, AI Quantum Convergence in Cyber Defense and Space Technologies. First of all, hearty appreciations for choosing such a title, because I feel that this FTP is at the intersection of two transformative frontiers, kind of, because it is AI and quantum computing. So today, as we move on to most of the hyper-connected systems, kind of, and data-driven ecosystems, so we find that the complexity of all the cyber threats that we see, it has grown exponentially, and it is growing exponentially on a daily basis, hourly basis, every minute on minute, and so on. So what I should say is, the classical computing techniques, what we all are aware of, is no longer going to be adequate to protect the critical infrastructures, especially the defense networks and satellite-based communications. So what I should say here is, this quantum intelligence, it is emerging not merely as an advancement, because everywhere we talk about the quantum algorithms and technologies, but this is the strategic necessity for the future and for the present. So with this given as the context of the FDP title that the department has chosen, we are also very privileged to have with us a very highly accomplished resource person. I hope most of you would have seen the brochure of all the resource persons who are going to deliver the sessions for this FDP. And they're all leading experts in quantum technologies, I can say cryptographic analysis, defense applications, and many other domains. So I'm sure that their knowledge and experience will inspire all of us to think beyond the boundaries and explore the immense potential in this evolving domain. So I request and encourage that all the participants will make the best use of all these sessions. I know it is raining outside. There is some cyclone announcements. But despite, I'm happy to see these many participants being present in this FDP session online. So even myself, I had lots of technical issues for logging in, but I feel happy after seeing quite a good number of participants in this particular session. So I request you all to ask questions, discuss ideas, and immerse yourselves in this particular learning journey of the 5 days the Atal FDP. I'm sure that the insights that you gain here, it is not only going to enrich your academic pursuits, but also it will shape our research pursuits. On behalf of Panimalar Engineering College, once again, and on behalf of the Department of CSE, Computer Science and Engineering, I extend my heartfelt gratitude to AICTE Atal for providing us this platform, and to each one of you for your valuable presence, because without you, this FDP is not going to see the limelight. And once again, I wish a grand success for this FDP. And let us begin this FDP with a good curiosity, enthusiasm, and a shared commitment for innovation and a good learning. And let us all strive to have a secure and intelligent future. Thank you, and wishing you all a very fruitful learning experience. Thank you all. Over to Satish, sir.
Thank you so much, ma'am, for letting us know the importance of this FTP and being motivational as well, always. Uh, uh, Mani, Principal sir, let me call upon our Principal sir, Dr. K. Mani, to address the gathering. Mani sir, are you there online?
Yeah, good evening all.
Thank you so much, sir.
So
Yes.
the Department of Computer Science and Engineering is organizing the AICT sponsored adult FDP program on the quantum intelligence. So it is a combination of artificial intelligence and quantum computing. So as we are aware that earlier, if we want information on any particular topic, so we all went to the library and referred textbooks. But nowadays, we can sit in one place and we can get the information on any topic using the AI platform. But the information given by the AI platform may not be correct always. So from our side, faculty side, we need some knowledge to decide whether the information is correct or not. So we needed to update the domain knowledge. So this quantum computing and artificial intelligence applications in cyber defense and space technology. So both are broader domain. So this 1 week may not be enough to learn in depth, but I hope this 1 week FDP on this topic will be an eye opening to all the participants, those who are willing to enter into this domain, which will be useful. And also, if you want to get information on any topic, right? For students also for learning, they are using this AI platform for coding, for writing assignments, and teachers also using this AI platform for the content creation and also for research. So there are tools available to carry out the research work. So faculty they are using, but the information available is correct or not, we should decide. We should have a domain knowledge. So there are many domains coming up every day. So we should learn all the domains as long as we are in the teaching field. So I hope this 1 week FDP will be useful for all of us to learn the new domain topics. So I am very happy to welcome the faculty members and all the research scholars and also industry participants for this 1 week FDP. So wish you all the best. Thank you. Over to Sadiq sir.
Satish sir, your mic is muted.
Okay. Thank you, Balaji, sir, letting me know. And thank you so much, sir, for briefing about this stage FPP and knowing that you're telling us the importance of it, and it has been motivational. I request all the participants to switch on their camera for the moment to capture this beautiful picture of the session, please. Please, participants. Participants, I request everyone to switch on your camera. So we'll take a screenshot of the session. Thank you so much, sir. Kumarasamy sir, thank you so much. Other participants, please. Please, just for a moment. Participants, please, I request everyone to switch on your camera.
Satish sir, okay sir, we can.
Shut up. Thank you so much.
Satish sir, we cannot hear.
Thank you so much for the. Can you take the screenshot of it, sir? Am I audible, sir?
Ah, yes, yes,
Yes,
yes.
sir.
Thank you. Thank you. Thank you. Okay, thank you. Thank you, participants. Thank you. Thank you so much. So now I would like to invite Dr. G. Senthil Kumar, Professor, Department of Computer Science Engineering, to welcome. Now I'd like to invite Dr. S. Balaji, Professor, Department of Computer Science and Engineering, to give citation and introduction about our first day chief guest.
Thank you, Satish.
Thanks.
It is my privilege to introduce Dr. Divyansh Shrimali, project engineer from CDAC Bengaluru, an accomplished researcher in the field of quantum information science. Dr. Shrimali's work spans critical areas such as quantum speed limits, quantumness of observables, entanglement capacity, and quantum technologies, with several notable publications in reputed international journals. His contribution to impactful research in the foundation of quantum theory, and he plays a key role in national level quantum technology initiatives and delivers expert training sessions on advanced quantum algorithms and applications. We are honored to welcome Dr. Shrimali today and look forward to the valuable insights he will share with us. Dr. Divyansh Shrimali, sir, you can take over the session now.
Yes, sir. Yes, sir. I hope I'm audible.
Yes, sir. Very much.
Yes, sir.
Okay,
Yes.
so I will try
Yes,
to
sir.
share my screen now.
Yes, sir. Okay, fine, sir.
You can see my slides, I suppose.
Yes, yes, sir. Yes, sir. Very much.
Okay.
Thank you. Thank you so much. Sir.
And
Thank you so much for accepting our invite,
yeah,
sir.
yeah, sure.
Thank you.
No problem. I'm honored to be a part of this FTP program. I thank your department at Panimala Engineering College for inviting me, giving CDAC Bangalore an opportunity to be a part of this AICTE funded FTP. So the topic today is like the 6 days that we are going to have the sessions at this FTP concerned with quantum intelligence, AI, quantum convergence, and cyber defense and space technologies. So when I see this with reference to encryption and decryption problems, I see that even this video communication that we are having right now, it's as of now uh, like in continuation, it's being encrypted by a protocol that is very much in use in encrypting every useful data that we have, whether it be of this video transaction, whether it be our bank, the money that is secured in our banks, whether it be some internet websites that we use on day-to-day basis, all of them are banked on RSA encryption scheme. So the reason why we trust that RSA is something that gets vulnerable when quantum machine comes into the picture. So that is the focus that I have for my contribution towards this FTP sessions, and I would like to give a talk on Shor's algorithm. So this is my title of the talk: "It's cracking the code, Shor's algorithm, and quantum period finding using Universe." So I think that I have given the context of the talk, why I have chosen this particular algorithm, this particular topic to move ahead in this session. I know that it's an afternoon, it's a late evening for all of us, and we had a busy day of work. So I would not be going into much of mathematical detail. There would be mathematical elements, but it would be giving a more qualitative picture of how things are and what is at stake here, what are the vulnerabilities, and what happens now. Now we are here. Now the encryption is at stake or it's vulnerable. What are the things that take off from this point? So the quantum toolkit here is the Shor's algorithm itself. So we will see how the particular Shor's algorithm is being constructed and how it makes the RSA encryption and the elliptic curve encryption, which is of use in our day-to-day useful encryption of internet and banking sector, how this algorithm actually works. This is something that I'm going to tell you. And then I will be demonstrating on our proprietary software development kit, which we call it Universe, on which you can actually play around with a lot of algorithms that there are and learn how quantum computing is done by the simulation that we have. And then comes the reality check and cyber defense implication of RSA getting vulnerable. And then I will be concluding the talk. So the current paradigm is RSA and the hardness assumption. So RSA, you know better than me because it's a department of computer science. So the concept here is that it relies on the asymmetry security. So if you are having the set A to set B, the one-way direction of going from like code, like domain to codomain, or from the domain to range is easier. But from range, if you want to go back to the domain, if A to B is easy, but B to A is not easy. So that is the asymmetry, which is the holy grail of the security that we have with respect to the RSA-based encryption. So as I said, most of the modern internet security, banking, VPN, all of them rely on the public key cryptography, which is RSA scheme. So the mechanism which RSA uses is of having two key sets. First is a public key, second is a private key. The public key is something that it broadcasts to the common public. People can eavesdrop, people can get that information. And the trust is that even if those people have the public key, the amount of time it takes to break the encryption using that public key and assuming and guessing a particular key which is not with them would be difficult, would be very difficult. So this is known to everyone. The private key is the key that is used to decrypt. So public key is used to encrypt the data, and private key, which is with the bank and is in the, let's say, the ATM card of yours. So that is the one which is used to decrypt. So it's as if like we are unlocking the box, which has been locked by public key. So this is kept secret. And how it is kept secret is because like the encryption is such that if you want to get the private key, the amount of calculation you would have to do is humongous. So in that way, the encryption protocol is secure. So as I said, it's a one-way function. RSA relies on math operations that are easy to do in one direction, but near impossible to invert without any specific hint given, which is the private key. So the mathematics is the trapdoor here. So the easy direction is we multiply. So let's say we have two large prime numbers, P and Q. So multiplying P and Q is not a difficult task. A regular laptop can multiply two 2048-bit numbers. 2048-bit numbers, as you know, goes as like 10 to the power 667 or 666. So it's a very huge number. So even if those huge numbers are there, but our regular laptops can multiply these two numbers very easily. It happens in microseconds. But the hard direction is the factorization one. If somebody gives you this capital N without giving you the P and Q, that would be a very difficult problem. To find those P and Q would be a difficult problem. So this is a computationally intractable for classical computers. What are classical computers? Classical computers are the ones which we use on our day-to-day basis, in which we retain our information in forms of bits. Bits store the value of the information in either 0 or 1. They're binary in nature, right? So that's what I mean by classical. Classical means if some bit is at the value of 0, it is at value of 0, whether you measure it or you don't measure it, and the act of measurement is not going to change it. Right? Now, computing, like classical computing, is at a particular juncture, particular area, stage where we have essentially weeded out all the noise that crept in during the classical process. So it's pretty noiseless. We have tamed the noise. The community has tamed the noise. So classical computers in that way are very robust. But there is a intractable factor when it comes to the number of operations that it can do. And surprisingly, the number of calculations that you have to do for factorization meets a particular roadblock, which classical computers are not able to take. So the hardness assumption, I will repeat, RSA is a secure because classical factoring scales super polynomially. I will come to that super polynomial factor. Factoring a 2048-bit number, which runs like 10 to the power 6 digit, would take trillions of years for classical computers to actually do. So this is the assumption because of which we rely on RSA encryption so much. Now enter the quantum threat, the short circuit. So the paradigm shift actually happened back in 1994. So Peter Shor, he was a computer scientist as well as a mathematician as well as an enthusiast in quantum information. So he worked at Bell Labs and he was trying to figure out, because as physics students or physicists, what we actually do is that if a problem is given to us, there are 2-3 ways we approach at the problem. If it's a potential kind of problem, we try to to approximate that potential with a quadratic like form. And when a pattern is given to us, or when a let's say when a seed is given to us, or when something is given in which we have to find the pattern, what we do is we just do Fourier transform. So that was a classical tool that people use. Now he was curious that what if we apply like a Fourier analysis on the wave function in which we actually encode the classical data. So what I mean by that is that if you are given a capital N, a value which is like 2048 bit digit, you somehow store that string in terms of a wave function. So you can do that. So let's say, I will tell you more about that during my demonstration of Kiniverse. But a number 4, for example, which is written as, or number 3, for example, in binary notation is written as 1, 1. It is very similar to writing it as a ket1 tensor a ket1. So it becomes a 1, 1 ket. So a single a 2-bit binary string, which is 1, 1, translates as a ket11 in quantum information or quantum mechanics. So he was curious and he just applied Fourier analysis on the wave function, and then through a clever set of steps, he realized something that, okay, there is an application of period finding which relates to factorization of the problem. So that is what exactly he did. So the breakthrough happened in 1994. Peter Shor, he demonstrated that a quantum computer could efficiently solve with factorization problem. So he was curious at a physics problem, having its application in encryption in mathematics, relevant to like computer science also. So suddenly when he realized that, okay, his mechanism or his method can solve the factorization problem in an efficient way, the quantum computation moved from a completely theoretical domain, physics, to a national security concern. Because every government data, every banking sector, financial data, even the SWIFT mechanism also relies on RSA. Yeah. So all of that became like vulnerable because of this algorithm. So he was invited at talks at FBI and NSA and lot of these organizations, and he had to explain that the threat is real. So what is the gap that he fit? So the complexity gap here is that the best known classical algorithms, which are supposedly like if there is a digit n, which means like if the n is is the characteristic or n signifies the number of bits that it takes to encode a particular number in binary string, let's say. Hello, is there a problem? I'm audible, right?
No, sir. No, sir. No. Yes, sir. You can continue.
Okay. So the best known classical algorithm, which is called general number field sieve, GNFS, runs in a sub-exponential time. So you see, there is an order of exponentiation of this n to the power 1 by 3 log n to the power 3. So this exponential of n is important here. So as the number of bit strings that are required to encode a particular number n increases, the complexity exponentially explodes. So the number of steps also would exponentially explode. And if there is a finite amount of time, which there is on our classical computers, this finite amount of time also exponentially increases, and that would run into a ginormous number of amount of time that would be impractical to break the encryption. Then there is Shor's algorithm. This is the one which quantum advantage came in. So this runs in polynomial time. So he proved that his algorithm took only order of n cube steps. Or with optimization, we can further reduce this complexity to order of n squared log n. So there is not an exponential factor anymore. There's no e to the power n or some constant to the power n. There is just n squared. So basically it's like a NP looking problem. It's not an NP problem. It has not been proven yet, but an NP looking problem has been converted into a P kind of problem, and that was a very significant moment in terms of quantum computation. So n, of course, is the number of bits in the integer capital N. So the implication for cyber defense. So this leads to, theoretically speaking, this leads to collapse of the public key infrastructure. Virtually all PKIs used today relies on two problems. First is integer factorization, RSA, and second one is discrete logarithm, which is the elliptic curve cryptography. I will not be delving into elliptical curves, but his algorithm directly targets this elliptical curve cryptography also. So Shor's algorithm solves both of them efficiently, making an NP looking problem into a P problem. So now we don't jump with joy. We also have to look at the reality of the situation. If a fault-tolerant quantum computer is built, a 2048-bit RSA key, which would take a classic computer trillions of years to crack, it can be broken in a matter of hours. So this is the reality that comes in, but the main essential word here is the fault-tolerant quantum computer. So this is something that I would be coming back again. But once we have a robust quantum computing system with a few, the number is significant, but with those many resources or those many quantum qubits, we can actually break the encryption that we are using in a day-to-day basis. So that is the point that I wanted to get here. So Shor, what he does is he manipulates a quantum superposition and entanglement. So entanglement is a phenomena which is very much essential for the success of almost all the algorithms and which are used in quantum computing. So there is a phenomena called superposition. There is a phenomena called entanglement. So let's come at superposition. Superposition principle basically says that so if somebody is giving you a state which is, let's say, a single qubit state written in alpha 0 plus beta 1, so that means that if they are in superposition, that means that before the act of measurement, you don't know in which of the state it is in. By that, what I mean is whether it is in 0 or 1, we don't know. So it's in a superposition. The act of measurement actually forces it to assume one of the states of 0 or 1. Entanglement means that if two particles are entangled and I retain one element here and send the second element arbitrarily far away, entanglement theory says that if I conduct measurement on my entity, my element here, it would have an instantaneous effect on the second entity, no matter how far away it is. So that is basically the crux of entanglement. So what Shor did in his particular algorithm is that he made clever use of the quantum superposition as well as the entanglement. He manipulated that, and he found a shortcut to the math complexity that protects the internet. So, uh, so field safe method is a bit more intelligent than brute force method, but the complexity is nearby. So the process which the method that he came up with using quantum superposition and entanglement, it skims through that. It circumvents that brute force method or those classical methods which were mired with the complexity of exponential complexity. So the blue line of the graph you see on the right hand side, we are plotting both the complexities here. The orange line being the Shor's complexity, and the blue line being the classical complexity of the best known algorithm. So the blue line of the graph is our best classical supercomputer running GNFS algorithm. That is the network sieve method. So as key size grows, which is in the x axis, so that is the composite number. So this small, forget about this small n here, like it's like capital N. So this is the number that we are having. So for and 10 to the power 166 is basically the kind of number we use for our RSA encryption, 2048 encryption. So you see, the number of steps goes from around 10 to the power 10 to somewhere around 10 to the power 8 or something. So this is like 100-fold increase, 1,000. Yeah, it's like 100-fold increase, 100 times like better performance with respect to the classical algorithms. So this is the factor that makes it vulnerable. But so far, when this Shor's algorithm was not in the picture, this complexity of the number of steps that were essential to be taken, so that made us feel safer. But the Shor's algorithm, turning this exponential problem into a polynomial problem, this turns an impossible problem into an easy problem, which scales in a manageable way. So this means that if a sufficiently resourceful quantum computer comes online, our current digital signatures and encrypted communications become transparent. As in, people with a particular machine, quantum computing machine, can break the encryption, and even this video feed that we are having, if we are trying to keep it private, somebody can break the encryption and can eavesdrop our communication over here. So now let's come to a bit of mathematical insight, where I would tell you that how this problem of finding the factor of factorization can be reduced into period finding problem. So in the quantum algorithm, we don't go with the brute force method. Rather, we rely on the period finding method. So the insight is we don't attack the factorization problem directly, brute forcefully. Instead, we use a number theory in mathematics to transform factoring into a period finding problem. So mathematics is again at the heart of this procedure. So if you can find like how often a function repeats, we can find the factors. So that is the basic premise. So what is the procedure? So for a capital N that is given to us, what we do is we pick a random number, small a, which is co-prime to n. So that means that the greatest common divisor between a and capital N is 1. So there is no common factor between them apart from 1. 1 is a triple factor, so it doesn't count. So once we have chosen a particular co-prime number a with respect to n, we define something called as modular exponentiation function. So what is this modular exponentiation? So this is like f of x is e to the power x mod n. So this mod n operation, which I believe everybody here knows, so it is like trying to find out the remainder when we try to divide e to the power x with respect to n. So this creates a sequence of e to the power 1, e square, e cube, and all, because f of x we just increment x uh, in an integer fashion. So from modular exponentiation, what we do is we find the smallest non-zero small r, which we call the period, such that e to the power r is one model. So that means like this also means like when we divide capital N, we divide e to the power r with capital N, we get the remainder 1. So that is the meaning of this equation. Now, this is the part which is hard for a classical computer to find. But for some reason, for quantum computing, it's easier. So the magic formula after we get the small value of r is the one that is again a classical method, the classical post-processing. So we do the essentially difficult part of finding the period r using a quantum computer. Once we have the small r, what we do with it? Once we have this period r, and we make sure that the r is even. Okay? If r is odd, we change the a and again run the computation. But because it's easier for a quantum computer, which I will tell you how it is easier, we can run it with multiple a's and we can find our r, which is even in nature. So even if r is even, so when small r is even, the factors n are simply the factors of greatest common divisor between e to the power r by 2 plus minus 1, comma n. So that's why we needed the r being even, because we wanted to divide it by 2. So basically, so e to the power r equals to 1 mod n. So this gives you e to the power r minus 1 equals 0. E to the power r minus bar by 2 minus 1 times e to the power r by 2 plus 1 have to be some multiple of this capital N that we are trying to find. So k is again an integer. So once we have the r with the chosen a and the given capital N, we can easily find out the factors that we want to find. And the moment you get the factors, you break the RSA encryption. So that is the crux of the idea that this algorithm is trying to get at. Now, you might get a question that again, we are relying on a particular function. Is it not complex? The answer is it's not complex. So there is an Euler's method for GCD finding, and this is always polynomial in nature. So it is as easy as any other polynomial problem there is. So we don't need better algorithms to tackle this particular. There's already very optimized. So this GCD finding is the one that we use in classical post-processing, and the holy grail of the algorithm is all about finding this small r that is the period in this particular sequence. So the middle procedure is classically hard but easy for quantum computers, and that's what makes the algorithm work. So now let's come towards how the algorithm actually goes about finding the small r. The idea, as I mentioned earlier, about Fourier transform. So the intuition is coming from the frequency. So we make use of Fourier transform, but here, because we are encoding the information in terms of quantum states, we call it quantum Fourier transform. So why QFT exists here? That is something that we are going to get at. So in Schur's algorithm, we create a quantum state that is perfectly periodic. So it repeats after every R steps. So in the normal basis, it looks completely uniform. So what I mean by periodic. So as you can see this function here, f of x equals to ax mod n. So when I write, it creates a sequence of e to power 1, e to power 2, e to power 3, up to some small r. So e to the power small r. After that e to the power small r is again 1, right? So that is the thing. So our goal is to find e to the power r equals to 1 model. So when we divide this e to the power r by capital N, we would be getting the remainder as 1. So that is the main idea. So the moment you do e to the power r, the sequence is again going to 1. So that's the meaning of what I'm saying. So there is a repetition of pattern here. So that's what I've said. So it creates a quantum state that is perfectly periodic. It repeats after every r steps. I will be telling you how that particular A is encoded in terms of the quantum state. In the normal basis, it looks completely uniform. So it is a flat, boring, no information kind of stuff. So you look at the wave on the right-hand side of the state in the diagram. So when you look at the collection of the frequencies, the main pattern that we are trying to get at, so it looks sort of something that we don't understand at the first look. But the moment we do a Fourier transform, it gives you these spikes. These spikes tell you what are the particular frequencies we are dealing with, and this dotted lines, these get for a particular frequency, this get at the waveform that a particular frequency carries. So with that, what we understand is that this pattern that we saw in a very haphazard fashion, this was in turn a superposition of two very nicely behaving periodic looking waveforms. So that is where Fourier transforms help us to analyze a particular curve or a wave by resolving it rather in terms of the constituent waves that we can easily understand. So this is what exactly Fourier transform does. So here when we use quantum Fourier transform quantum Fourier transform is the quantum version of hearing the notes inside the chord, right? So we hear the sequence. Now people may not be able to understand where that sequence is actually coming from. So the quantum aspect of the quantum version of this particular chord, when we do the quantum Fourier transform, we get the notes that make up that particular music. So that is what we are trying to do. We are converting the mathematical problem of factorization into a music analysis, if you will, right? We are trying to get those frequencies, those phases that will be helping us to figure out the factors that are involved and ultimately solve the RSA encryption or decrypted. So after QFT, huge peaks appear exactly at multiples of 2 to the power n by r. So we measured this particular function. Small n is given to us. By that, we can get r immediately. The moment that is done by classical cross processing, we are able to break the encryption of RSA. So it's important. QFT doesn't search. It physically cancels the wrong periods. So once you look at the QFT, once we do the quantum Fourier transform, the output that comes in, that is not the solution. Okay? That helps us to get to the solution. It gives you a pattern. Looking at that pattern, you get your value of R, and that you solve to that you use to solve the factorization problem. So it just physically cancels the wrong periods. It uses destructive interference and amplifies the correct one, that is using the constructive interference. So only those frequencies here in the Fourier transform also what happens? The frequencies which are not present, they destructively interfere and they are removed, but only those which are a part of the waveform, they only remain, and that is the constructive interference that is at play here. So it is very physics inspired, and using mathematics, like mathematical theory of number theory, converting factorization problem into a period finding problem, and using physics principles of Fourier transform or quantum Fourier transform in a quantum computer, we are able to break the encryption. So it is a very beautiful overplay of mathematics and physics in conjunction which is solving the security, which is kind of breaking the security of RSA scheme. So classically, we would have to test millions of possible periods. So that is the part which makes it the period finding part classically hard. But quantum mechanically, the interference does the job in one shot, and that is the beauty of quantum mechanics. That is the beauty of quantum computing. So a bit about quantum Fourier transform. So we have a state J. Now the state J is again that thing that I told you, that if you are encoding your, let's say, a number like 4 or number like 3 in 1 1 or number like 5 in let's say 1 1 0, that kind of like binary encryption. So that particular bit string can be encoded in terms of a quantum state. So that is the representative of in form of this get vector, that is the J vector here. Once we take the Fourier transform, this is the superposition form that it comes in. So it is just saying that there are particular exponential terms which are the phases, and these phases have to do with the vectors that are there. It's very much similar to usual Fourier transform. So the sum goes from 0 to n minus 1. So there are capital N number of superposition terms here. So capital N is to the power n. We have n qubits. We make use of n qubits for capital N possible basis states. So basically what it means is, let's suppose we are trying to factor out a small number. Let's say the number is 21, right? So 21, so what is the closest small n, so that 2 to the power n is just more than 21. So the answer there is small n is equals to 5, because 16 and then 32. So 32 is the number that we are looking at. So for trying to factor out a number from, let's say, 17 to 31 or 32, we make use of 5 qubits. That is the meaning of small n here. So QFT takes any basis element I and spreads it evenly over K with carefully chosen phases. So this is exactly what it does. So it takes a particular state I and it does a quantum Fourier transform. And because owing to the structure of this summation here, so we now have a superposition of capital N number of states. And each of those states will have a corresponding coefficient, and those would be acting as phases here. So the phases are exactly the same as the discrete Fourier transform. So when the input state is periodic with the small period of r, the phases line up perfectly only at some small k, where small k is approximately s times n by r. So capital N is given to you. S is the thing that is associated with the pattern, and small r is the period that we're trying to find. So basically, this S actually varies from 0 to R, and that's how, or from 1 to R. So only at n by R, 2n by R, 3n by R, 2. So these are the factors on which we will get the particular peaks, and all the wrong k values actually cancel out. So this is what quantum Fourier transform does. So quantum Fourier transform is nothing more than a controlled interference. So it forces all wrong answers to destructively interfere to almost, it leads them to 0, and only the correct frequencies they add up coherently, and only they are the ones that are retained. So we make a note over here. We never compute this sum explicitly. The quantum circuit applies it in place using order n square gates. So you see, so the job is actually done by the gates. We don't do it explicitly. We don't sit out and do the mathematics or do the matrix multiplication by our own. We just arrange those n square number of gates that are required, and n, as you see, grows as logarithmically as the number size increases. So capital N, if there is a capital N, so the number of qubits that we will be requiring goes like log of n. So it's like log n square complexity. So that's again a very manageable number, right? So only those number of gates are applied, and owing to the character, owing to the quantum feature, it's a one-shot calculation for them. This is not comparable. The complexity is nowhere comparable to the classical case that we had. So this is the exact exponential speed up that Shor's algorithm comes up with. Now let's look at the quantum Fourier transform is there, but how we actually make use of this quantum Fourier transform to get that particular value for R. So that is done by something called quantum phase estimation. So this is the heart of Shor's algorithm. This is the one that we all actually would want to achieve with when a fault-tolerant quantum computer comes in. We would want to convert every problem into a QPE, and that's exactly what Shor's also did. So he converted this this pattern finding problem into a QPE problem, and then he found the solution with this by getting the value for. So how does it work? So the phases that arises from Fourier transform get written into the register by a phase kickback, so which makes period finding possible. So what we are doing here is that, let's say we have a state psi on which we have this particular number n, right? And we make use of m number of registered qubits, okay, on which we want to encode the information of small r. So again, so the small psi or the vector psi is such that we make use of this particular psi to somehow get the value of r. So how we choose this particular psi? In quantum phase estimation, what we make use of is that we try to build up a particular unitary operator, a unitary gate, a control unitary gate rather, such that this psi is an eigenstate of this U. So basically, psi is constructed as an eigenstate of this U, and this is not a difficult problem. The maths of that I'm not going to detail. It's a bit more complicated, but as of now, assume that with n number of qubits, small number of n number of qubits, you prepare a state psi, which is an eigenstate of the unitary operators that you're going to make use of. So once a unitary operator applies on this state psi, it just makes just okay. So it just gives out a phase factor of e to the power 2 pi I phi. So our goal is to find out this phase phi to high precision. As I said, this phi. Okay. So e to the power 2 pi I jk by n. So this is the 2 pi I phi term. The jk by n is the phi term here. So this is what we are trying to figure out here. So Fourier transforms just encodes the coefficients with each of the gates k. It's our job now to figure out what those particular k's are, and that is done via QP. So that's where I'm getting at. So we have to estimate this value of phi, and that is what the circuit is actually implementing here. So the top register is the counting register. So this is the counting register that actually encodes that information of R in this vector of phi. So what we do is we start in uniform superposition via Hadamard's. So let's look at this circuit one second. So what we are doing is we are applying Hadamard operation on each of the qubits here. I will tell you in my universe demonstration how the edge actually does its job. But as of now, just understand that once we apply all these Hadamard operations, what it does is it makes possible all the superpositions to be considered in a parallel fashion. So then what we have, once we have all the superposition of all the states possible out of m number of qubits, we make use of controlled unitary operations. So it is saying that, when the first line or the first qubit, when it is 1, then a unitary operation U would be applied on psi. because U is a let's say the psi is an eigenstate of U, so it will not be tinkering with the psi. It would be just giving it a phase vector. If the second qubit is 1, then it would be applying a U square operation and so on. So the third qubit, if it is 1, then it would be applying a U to the power 4 operation. So it's like, it scales like U to the power 2 to the power n, right? Or 2 to the power k. So when k goes from 1 to n, it goes from 2 to the power 1 to the power 2 to the power k, number of applications of U operations controlled on these M register states. So once that operation is done, surprisingly, there is a phase kickback, and because of which, once we do the quantum Fourier transform, inverse of quantum Fourier transform, so quantum Fourier transform, what it did was it got your J from J to K superpositions. So capital N number of superpositions were there. Once we do the inverse quantum Fourier transform, what it does is, like, it does the like constructive interference on the good states and destructive interference on the bad states, and it only retains the good states. So that's what the inverse quantum Fourier transform does. This is the holy grail of this algorithm. So that's why we make use of inverse quantum Fourier transform. Okay, so the bottom state, the eigenstate U or the psi of unitary U, is a periodic state. So QP writes this unknown state phase of phi into the amplitudes of the counting register. So once we measure these states, this M states, we will be getting those many peaks that would be corresponding to the number of peaks that we should be getting, so that we can estimate the value of small r. So after inverse quantum Fourier transform, this dagger operation is just saying that we have quantum Fourier transform, the dagger is the inverse of that. That's why I'm calling inverse quantum Fourier transform in terms of quantum Fourier transform adjoint or dagger. So after QFT dagger, we read this theta or phi as y by 2 to the power m, where y is a binary number of either 0, 1, 2, or 2 to the power m minus 1. So in terms of binaries, it is. So how QP and QFT actually find the period? So I will again go through that. So we have controlled unitary operations, which are like 2 to the power k operations. They kick the eigenphase phi into the counting register via phase kickback. And actually happens, you can see the mathematics of it. So after kickback, the amplitudes are still uniform, but the phases now contain the phi and the Fourier basis. The phases are unreadable in the computational basis. So the probability actually looks flat, but the inverse quantum Fourier transform rotates those states and converts the hidden phase into a huge probability peaks at the correct multiples of 2 to the power m by r. So inverse quantum Fourier transform is actually just reading the phase. It is not giving you the phase directly outside. It's just reading the phase. It's only when we do a repeated number of measurements that we get the outcome in terms of histogram plots. From there, we actually estimate, okay, this is the value of r that I'll be demonstrating shortly. So it turns the invisible phase pattern into a visible probability spikes we can measure in one shot, right? So from psi 0 to psi 1, this is the phase kickback things from psi up to psi 2, sorry. So with respect to all these unitary operations, which I'm designating and just one block of UF. So till phi 2, we have phase kickback. From phi 2 to phi 3, we have phases and Fourier basis that we have to understand. And after we apply the inverse quantum Fourier transform, we decode that particular phase to get normal integer. And that's the whole operation of this algorithm. Now, the modular exponential operator, which is the integral part here, the unitary U. How would you construct that particular capital U? So this is the black box of Sugar. So the black box operations are the ones which are, in general, they are theoretically estimated to be a particular function or a complex set of gates that would be working for any particular given A and for any particular N. So that is a complex entity in itself, but that has been constructed and that is not impossible to construct, at least in the Shor's case. So the unitary operator UA is the black box, and it's also called the oracle. What it does is when a UA operates on the get X, what it does is it takes this get X to X dot A mod N. So it just multiplies X with A. If there was a U A or A U subscript A to the power K, it would be multiplying X with A to the power K and then trying to get the remainder with respect to capital N. So this is what exactly U is doing here. So control multiply by a modular N, and it's reversible and also unitary. So the eigenstate of UA, so we have equally weighted superposition of periodic sequence in an eigenstate. So let's say we have a state of US as like 1 by square root of R, get 1 plus get A plus get A squared plus get A to the power R minus 1. The moment you have A to the power R get, that goes to 1. So this is the general state, that is the eigenstate of our unitary operator. Once we apply the unitary operator AUA, it simply adds a global phase to all of these terms. So e to the power 2 pi is by R US. For some integer small s, that is co-prime with R small r. Otherwise, we would have just factored it out, right? So exactly the form we need for QPE. So phase is pi s by R. So this is the phase that we are trying to get. So how the model operation is done? We don't prepare the complicated US state by hand manually. We simply start with the very simple state 1 in the target register. So all our goal is just converting the one of the states. So here this information is a bit lacking. So what we do is that when we apply the unitary operation in the bottom part of the SHI that you look at, what we do is that on one of the on the last qubit, we just apply a phase flip we just apply a X gate. So it's just a flip operation. So the moment we do that, we just go into the state 1, right? And we start from there. We don't have to manufacture a particular eigenstate of this particular unitary operation. We have the unitary operation, model exponential operation, give it to us. We just initiate or start with the state 1. The moment we do that, we don't have to manufacture a complicated state. So we simply start with a very simple state get1 in the target register, because get1 is 1 by this number of eigenstates that is there, small s, number of small s, and we just get a superposition of US because these are complete set of states. So 1 is an equal superposition of all eigenstates of UA, right? So when we run quantum phase estimation with initial target state of 1, the counting register automatically picks out one of the phases S by R at random, exactly what we want. And it does it at random. So one run, it gives S by R, second run, it gives S dash by R. And when we do measure, we actually get those histograms corresponding to that particular state. And that's how you estimate the value of small r, right? So the takeaway is we never built the periodic state ourselves. We start from 1 plus Hadamard's plus model exponentiation, and automatically creates the perfect superposition of all the eigenstates. Is there a question in between? Somebody was raising hands. Hello? Hello? Am I audible?
Yes.
Yes, sir.
Yes. Yeah.
Yes, sir.
So there was some hand marks. So there were some questions which were coming in, or should I take them after the talk? Hello? Should I take the questions after the talk, or should I Should I answer them now? I'm asking.
Sir, after the talk, we can have that, sir.
Okay, no problem. So what we do is we start with state 1. We apply the Hadamard's, we apply the modular operations, and we then do the inverse quantum Fourier transforms. We do the measurements, and that's how we get the small r that we require. And QPE just extracts one of the periods r for us. So this is a full Shor's algorithm circuit. So this is how it looks like. So we initialize the counting register to 0, 0, and the target register to state 1. So we just apply one of the X gates to one of the qubits, and we get a state 1. And then we do a controlled unitary operations based on the register states output. And then we take the quantum Fourier transform, inverse quantum Fourier transforms, and that's how we get small r. So superposition, we encode the periods into the phases, we decode with inverse quantum Fourier transform, and we measure to get the period small r. Now let's try to figure out how this algorithm runs for capital N equals to 15, a very simple small case using Shor's algorithm. So for capital N equals to 15, we wish to find factors. I would be doing this evaluation for 2 of the choices. So let's say the choice first is a equals to small a equals to 2. The classical check is the GCT is 1, that's fine. We run the circuit, we expect the peaks. So the mathematics of it is if we measure output small x, the phase is S by R is approximately x by 2 to the power n, where x is a bit string, right? So that is something that we expect from the measurement. So we expect to get small r equals to 4. We can actually do the calculation. And because it's a very small number, we can actually do the calculation. And to check whether Shor's algorithm is running or not properly, we get this small r equals to 4 there. That's something that we have to demonstrate and verify. So by calculating this small r, we divide that small r by 2. So to the power 2 plus minus 1 is indeed the factors that we actually require. For a equals to 7, the case is a bit more complex. So GCD of this is 1, that's fine. So the circuit of it, it would be a bit more involved. So once we run the circuit, we again expect r equals to 4 in this case. So factors 7 to the power 4 by 2, that's n squared minus 1, 48. And the post processing is, we again take the GCD of this 48 with 15, and we get the number like 50. And again, when we take the 50 with like GCD of 50 with 15, we get 5. 5 is one of the factors, we can divide easily, and we get another factor also, that is 3. So now it's demonstration time. So let me change my screen. I hope my screen is visible, right? So this is our proprietary
Yes, sir.
software, which we call Quniverse. So first of all, I just wanted to mention that Supercomputing India, this symposium or conclave is going to happen, going to take place at MIT and Bangalore, which is organized by CDAC India. So if somebody is interested, somebody is willing to come in, we will be having esteemed speakers coming for this conference, giving very relevant talks, something which is concerning with the topics that are covered in this FTP also. So you can register and come here. And there is a 40% discount also that is running as of now. You can make use of this Quniverse. You can register and make use of this particular code to avail this discount. So let's go to Quniverse. Okay, so this is our software, Quniverse. So in this, what happens is that we can just drag and drop the gates and see how our states look like. So this is the manage section in which we can actually, let's say I'm working for only 1 qubit. So when I apply Hadamard, what I told you earlier was that Hadamard puts the particular state in superposition. So Q0, you see, is in a state of alpha is equal to 1, beta equals to 0. So it's just psi equal to 0 state, right? So once we have that, when we apply a Hadamard operation, we expect that would be a superposition of 0 and 1. And the phases, there should not be any phase with respect to that. So it should be just 0 plus 1. So how do you verify that? You go to the state vectors and you see that there are no reddish or greenish kind of lines. So it's saying that the phases are intact. The superposition is clean plus 1. But the moment you have, instead of ket 0, you are, let's say you're beginning with only psi equals to 1, right? Then what happens? Then when you apply Hadamard operation, then you see here that the phase has inversed. It's a 180 degree. It's a pi radian inversion. So this is a state which would be in a superposition, but it would be a superposition of ket 1. Hadamard operating on ket 1 would be giving you 0 minus 1 by root 2. And that's how the phase thing comes in here. You could have done the exact same thing by applying a X gate also. So you see, for 0 ket, again, you are getting the same states. But when we apply a phase, when you apply an X gate, which is a bit flip operation, so when bit 1 is applied on, let's say, 0, it gives you 1. When it would be applied on 1, it would be giving you 0. So on ket 1, when you apply Hadamard operation, then you see, again, you get the phase inversion here. So it's again 0 minus 1 by root 2. So that is one of the gates. Then there are many other gates. So I can increase the register size. You have to read the state from right to left. So this is the first qubit, and only on the first qubits we are applying the operation. So this is like 0 plus 1 by root 2. Other two are just tensor product. They are not something on which gates are operating, so they are just on the side, so nothing is happening on them. So the moment you remove that, you again get 1. So that is the operation here. So I mentioned something about entanglement, right? So what is the entanglement? So for producing an entangled state, what you do is, okay, save it. So you had Hadamard operation. For creating an entangled state, you have to make use of interaction between the two qubits. So far, when you have no C0 kind of gates, you see there is a controlled operation here. So based on the output of this particular qubit, an X gate is going to be applied on the second qubit. If it was 0, which is set like ket 0, then you see that nothing would happen. It would be just a 0-0 state. But the moment you apply Hadamard operation and put it into a superposition, now at this point it is no longer just 0 ket, it's 0 plus 1 by root 2. The moment you happen to do that, and then you apply C0 operation, you get an entangled state. So this is the entangled state. 0 plus 1 by root 2. And by probability distribution, what I mean is that when you do the computation, when you make use of the like measurements on these particular states, this is the distribution that you will be getting. Because it's a noiseless simulation, so we are just having an ideal situation over here. Now, there are many other gates also. Let's go to a 3-qubit gate for demonstration purpose. So I told you about C0 operation. So it's a control operation. Similarly, we have Toffoli operations. What Toffoli does is that if these two operations are 1, then it will flip the third qubit. So what I mean by that is that once you apply these this X gates on first and second qubit, then it would be flipping the state of the third one. So this is what it does. So this was 0 ket, this became 1. If you apply, just to check it out, if you apply an X gate on the third qubit, it would make it 110. So now it is 1, 1, 0. You have to read it from right to left. So this is a Toffoli operation. There is one more operation, which I call as control swap operation. What it does is, so if this particular particular qubit, let's say it's C, then it would, if it is 1, then it would flip the output of A and B. What I mean is, by this is like, if on the third qubit, because the control is on this, right? And the target are the first 2 qubits. So if the control is 1, then it would flip it. So let's say I'm having this particular state. So the input state is 101, right? 101. Now see what happens. It becomes 011, right? So it just flipped the operation. Now, why am all of a sudden I'm talking to you or telling you about a control swap or a Toffoli gate? First, I want to make you appreciate the complexity of these kind of gates. Let's say I'm talking about a Toffoli gate. Let's see how it looks like. This is the circuit diagram for a normal Toffoli gate. It's not very essential, but I feel that this discussion would be incomplete without telling you this. The complexity of quantum computing also comes in because we have to make use of something called as Clifford and T gates, right? Clifford gates are the one which are somehow, so whatever the Clifford gate does, we can do it in polynomial time, but it is only the T gates which are going to make the real quantum advantage come in, right? So Toffoli operation involves a 1, 2, 3, 4, 5, 6, 7. So there are 7 T gates which are involved for a Toffoli operation. So, and there are 1, 2, 3, 4, 5, 6 entangling or C0 gates. So interaction gates are 6 and T gates are 7 in number. And apart from that, 2 Hadamard operations are there. So this is the complexity of the number of gates that are involved in a particular circuit, right? And this control swap operation, this itself is made up of 3 Toffoli gates in a reverse order kind, right? So the control is A here, the control is B here, again the control is A here. So there is a swap of controls in the Toffoli gates, and that's how the control swap operation comes in, right? So why I'm telling you all this? Because I want to make you understand this particular circuit. So what is this circuit? What is this circuit doing? This circuit, yes. So this circuit is the circuit for t equal to 2. So when I was saying that let's demonstrate factorization of n equals to 15 on our proprietary software, that's Universe. So this is the circuit that I meant there, right? Now each of these gates, like these custom gates that I've made, are sort of complex in nature, but because the number of qubits are less, so this can be managed. So far as of now, Universe is again in a development phase. We have a restriction that we cannot directly show you the number of qubits. Like if the number of qubits is more than 6, which is this case, the total number of qubits is 7. And for n equals 15, you need at least those many qubits. So this is the circuit for that. And unfortunately, we will not be able to show the distribution on the go, right? Of how the what is the outcome of running the circuit. But I want to make you understand how the QFT and QP operations are actually performed here. So you look at the diagram here, right? So what do we have? We have to start with the state 1, and how the state 1 is made. This is how the state is made. So there is a ordering problem here. So imagine this part is above and this part is below, right? So this is the register states. So we start with saying that, okay, this is my dominant one, this is my most insignificant qubit. This is the last qubit, right? So the moment you have the last qubit flipped from 0 to 1 and all other qubits or bits are 0, then the state essentially is 1, right? And after 1 comes 2 and 3 and so on, because we just flip the operations. So this is the state with which you begin, right? And then you apply Hadamard operations on all the resistor states. This is exactly what is happening. So on the 3 Ensla states on which you will be doing the control unitary operation, you see that we are applying Hadamard gates. For n equals to 15, what happens is, it's a beautiful thing, that you just have to apply only one unitary operation. All other unitary operations just like, hello? Is there a question?
Nothing, sir. Go on.
Okay. So the beautiful thing is that the complexity of the application of all the unitary gates reduces to just application of one gate, because when you apply another unitary gate, you come back to state 1. So essentially what it does is all the unitaries, if you just apply as it commands, then you would be having just a superposition of 1 and 2, 1 and 2. So that's why we can reduce the complexity for this particular case by application of just one unitary gate. I'm sorry. That happens with a equals to 4. For a equals to 2, it's a bit more complicated. So what happens is that you apply unitary gate, and what it does is that one unitary operation actually gives rise to superposition from 1 to 1 and 2. Then when you apply another unitary gate, that is a U square operation, and this is the control swap operation that I told you. What it does is, look at the third qubit here, the C qubit, which is the Q5. If Q5 is 1, then it will swap the A and B, the Q0 and Q2. If the in the state is 1 here in the C qubit, then it will swap the Q1 and Q3. Right? For A equals to 2, it's a bit more complicated. For A equals to 4, it was not. So I sort of confused, sorry. So I will call this circuit as N15A4 door slits. Right? So this is the control swap operation. And why this works is because for a very simple looking numbers like 1, 2, 4, 8. Okay, so essentially the game that we can play with these many qubits is that we just have to swap one of the bits. What I mean by that is that let's say you have a ket like 0001 and you want to go to a ket 8 from this ket 1, you just have to swap the first and the third qubit and the first and the fourth qubit. That kind of operation you have to do, right? So those operations are very easily, it can be done by simple swap operations. So this is the trick that we make use of because of the easiness of handling the bits, that we can simplify the calculation with making just these two kind of unitary gates. Otherwise, the number of gates that would be required, that would have been very much. For a this is the custom modular exponential operation. If we would have used the go to modular exponential function, the circuit depth would have been very much, as I would be telling you in the next section. Once you apply U operation, then this is U square operation. This two control swaps, they combine to make a U square operation. Then you perform something called as inverse quantum Fourier transform. Now let's see how it looks like. This is how it looks like. So you make a swap operation on the fourth and the sixth qubit, and then there would be Hadamard and the P gates. So what P gates is? P gate is a gate which just rotates the state with respect to Z axis by an angle of -5. So by doing this, the outcome would be registering of those phases in the state of in the form of small r. So that is something that we would be getting by IQFT gate. if you look at a QFT gate, let's say I'm looking at a QFT gate, how it looks like. So this is how a QFT gate looks like. So you apply, if a QFT gate is applied on Q1, Q2, it starts with a non-dominant one, add mod operation, P gate, and then add mod operation on the side. If I increase the complexity and say, okay, these many qubits on which I'm applying my QFT operator. So now what happens? So this is the complexity of the QFT gate. So this is the most insignificant qubit. And then I have to apply these many controlled P gate operations. And you see, for kth qubit, we have to apply K minus 1 control unitary operations. So for third one, we have to apply 2. For second one, we have to apply 1. And for the most dominant one, we don't have to apply anything. But the moment you look, and then we apply these swap gates because we have to reverse the order, right? So that inverse quantum Fourier transform can pick up from the right state. So I will just remove this one, and you again look at the inverse quantum Fourier transform. So this is just the inverse of that. So now we have to begin, we start with the most dominant one and go to the most insignificant. And this operation registers the value of small r in terms of in the string of these bits that you will be calculating. So now let's run this operation. Let's actually run it on an actual quantum computer, right? So while running, Universe provides you multiple options. You can run it on our proprietary CPU. You can run it on the GPUs that we have. We can run it on FPGA cards also, and we have the QPU that is that's the IBM SuperStack hardware. So it is just waiting for that to load up. So this is IBM Q as QPU. So once we submit it, so this will be running shortly. I'll just have to. I'll just give me a demo with one of them so that you'll be getting the idea, and then I'll be showing you the result. And you see that for equals to 2, we get indeed the value as 4. So the histogram, you look at the circuit. This is the circuit that we ran, right? There were just 2 unitary operations that were involved, that were required, U and U square. The moment you do U4, it comes back to this one. So this is basically that those many number of operations that you have to do, that is actually encoding the information of R itself in some way, and that is somehow what we are getting from these 3 register qubits. So these are the 4 spikes that we get, histogram plots we get. These many peaks that you would be getting from the measurement is indeed the value of R, right? The moment you get the value of small r, as like for 7, we get for that. So for a equals to 4. So for 4, we are getting the value of 4, and that indeed is the one that small r equals to 4 is indeed the one that will help us to get the factors of the circuit. So now again, let's load the thing, and okay, so this is the same thing. Let's load this one. Okay. So now this one, I suppose, is the one for a equals to 4. For a equals to 4, for a equals to 2. So here we just need one unitary operation, and when we ran it, okay, so right. So earlier one was a equals to 2, sorry, and this is one for a equals to 4. And for 4, we just a equal to 4, we just require r equals to 2, and this is indeed what we are getting. The earlier one, I'm sorry, this was equal to 2. That's why we needed 2 unitary operations. For this one, the circuit is actually easier. We just need 1 unitary operation, and we get r equals to 2. 4 minus 1 and 4 plus 1 are indeed the factors of the digit. So you see, for n equals to 15, it is way easier to perform these operations, right? So I demonstrated on Kiniverse how actually you get the factors for, let's say, a value of like n equals to 15. But if you want to go to some other number, like let's say 21, so why I did not demonstrate the working of the algorithm with 21? Because it isn't just adding one more number to that. So from 15 to 21, if you want to register this digit in terms of number of qubits, you go from just 4 to 5 qubits, right? But in terms of complexity, it is not that simple. So it's not just adding one more number. It actually requires a leap in resources. Because with 15, there was a very like beautiful property that 15 number has, that it is in the form of 2 to the power n minus 1. But capital N equals 21 is not that lucky, right? So for that, there are certain complexities that we'll be getting at. So the qubit requirement is the width, and for Shor's algorithm, it requires roughly 2 times n plus 3 qubits. And so this is the one that at most that would be needing. But you see, for our earlier demonstration, we didn't need 11 to 12 qubits. We needed just 4 qubits for the register states and 3 qubits for the phase kickback. So in total 7. But if you would have done that in the complex unitary operations that are open for all, then we would be needing actually 11 to 12 qubits. The other qubits would be the ancilla qubits. For n equals 21, unluckily, we have to make use of all the qubits. So even though the qubit jump seems small, the state space doubles for every qubit that is added. So circuit depth is the real wall. So the model exponential function is the main bottleneck. So this is the big, gigantic, complex unitary operation that we would have to perform on our circuits. So for capital N equal 15, the logical circuit is simplified by the compiler. For n equal 21, the circuit must handle general modular arithmetic, and that actually results in thousands of gates. So just like how I showed you for this a equals to 4 case that required just one unitary operation, and it was just two simple C0 operations. But for n equal to 21, these many gates will not suffice. We actually require a lot many gates, and I will be showing a small picture of that. So the complexity actually runs in thousands of gates requirement, right? Okay. So the result is that simulation time increases from milliseconds to minutes or even hours. So our Kiniverse platform actually can simulate the simulation of factoring those numbers. But for numbers that are not in the form of 2 to the power some integer minus 1 or plus 1, the complexity is such that the runtime is much more, because we actually have to make use of the actual unitary operation, right? So that's why, for demonstration purpose, n equals 21 is never used. It's only n equals 15 that is used all the time. So the classical limit is the state vector explosion. The classical simulator, like the one back in Kiniverse, must store the probability amplitude for every possible state. So in Kiniverse, how we are doing all the calculations? So these are just matrix multiplication. For each gate, there is particular matrix, right? Let's go to circuit. You look at the particular matrix. So how it looks like. Sorry. So this is the matrix. So we are just applying the matrix, right? Hadamard operation or the phase or the bit flip operation is again a matrix. So it's like 0, 1, 1, 0, right? Hadamard operation. These are again matrices. So it's 1, 1, 1, minus 1. So that's how we are doing the simulation here. So all of them involve matrix multiplications, right? So there's a problem with that with respect to classical simulation. Hello? So the memory required scales like to the power q times 16 bytes. So it's a complex double. So for 30 qubits, if you want to simulate 30 qubits, even a regular PC can work because we just required 16 GB of RAM. But the moment you increase that requirement from 30 to 40 qubits, all of a sudden you require 16,000 GBs of RAM and becomes a territory of supercomputing territory. You see, so that is the reason why we don't like we have a limitation with respect to small n number of bits that we can simulate or the number that we can break. Because if we are to make use of the Shor's algorithm, in simulation, we cannot even touch 50. It's near impossible with classical simulation to simulate 50 qubits, right? So CDAC's context is, while CDAC supercomputer Param series allows us to simulate a larger system, we eventually hit the exponential wall of around 36 qubit in our case. So the conclusion is we cannot simulate our way into breaking RSA. We need real quantum hardware. Why real quantum hardware is required? Because in real quantum hardware, there's no requirement of matrix multiplication. It has happens in one go, right? You have physical qubits. You give pulses through which they apply particular gate. They configure themselves in particular gate operations, and the circuit running is essentially taking no time. That is the real speed up that comes through only real quantum hardware, and it cannot come through simulation alone. So the earlier thing that I ran, if I would have, so that took classical post processing, and our code was also not very efficient, let's say. So the quantum part was done in a very quick time. But if I would have done that through simulation, it would have taken more time. So the simulation barrier is there. N equals 15 is a special case. It's of the form of 2n minus 1. So the multiplication logic simplifies drastically. For a equals 2, it effectively becomes just swapping wires. So a equals 2, it becomes just swapping wires. For equal to 4, we just needed C0 operations. So we didn't need to do real arithmetic, but just took shortcuts, and that worked. But the reality of 21 and equal to 21 is that it has no such symmetry. We must implement the full modular multiplier circuit. So the gate count explodes. So for n equals 15, with all those like all those C swap operations and QFTs and whatever, we just needed to make use of 21 entangling gates, which are 21 C0 operations. But for equal to 21, we actually require, and it has been calculated that we require actually 2005 entangling gates, and that's 100 times complexity increase. So simulating this classical requires matrix multiplications, which is too deep for real-time demonstration, and that's why people like simulation does work, but it may take unreasonable amount of time for a live demonstration. So classically simulating quantum entanglement cost memory exponentially. For n equal to 15, we just needed 4 qubits, kilobytes of memory. For n equal to 15, we are 21, we need 5 qubits in Ancilla. State vector is manageable, but the time steps to simulate around 2,500 gates. This drags simulation from milliseconds to minutes or even hours. The simulation barrier, scaling from n equal to 15 to 21, you see for n equal to 15, we have a very shallow and short circuit. For n equal to 21, this is not the point in which this circuit actually stops. It runs for at least 10 times more circuit depth, right? Because we have to make use of those 2,500 gates to implement that unitary operation. And that's what makes it so complicated. QFT is not difficult. Inverse QFT is also not difficult. It is the modular exponentiation which is the bottleneck here. It required those many qubits. Hardware reality. why we can't break RSA yet. Even the Short's algorithm promises, but because of the gate complexity, we have certain limitations. Ideal cases, clean peaks at period R, but real hardware results in noise, floor rise, and peaks get buried. So you see, for example, this particular plot. If the noise would have been a bit more than what it is, then we won't be getting this 001 and 111 state also. Or we could be getting some other states which should not be coming into the histogram. So that is the problem with the noise. So this is the real reason for concern, right? So how the noise actually creeps in our quantum computation? So it creeps in terms of decoherence. So there are two times which function as parameters that are involved. So in terms of like how we characterize the noise, the first is this T1 time. So what it means is that if a state is in an excited state, how much time it takes from jumping from this excited state to the ground state or to a state which is smaller than that. Then there is dephasing time. So let's suppose there is a matrix and it has the state, and the state is represented in terms of matrix, right? So if there are off-diagonal terms which are non-zero, right? So that means that there is a probability of transition between from one state to the other. But the dephasing, what it does is that it makes those off-diagonal terms as zero. So now the transition between state 1 to state 2 doesn't happen. And then essentially the superposition principle or superposition property is lost, and the quantum advantage will not be there. And then there are gate errors. Suppose I want to make a rotation of
You'll have
Sir, your mic is muted, sir. No, sir, it is muted still. Sir, it is muted from you, sir. Divanshu, sir. Participants, am I audible?
Yes, sir. Audible, sir.
No, sir, not audible.
Audible, sir. Now it is audible, sir.
audible now?
Now it's fine, sir. Yes.
Now it's okay.
Okay. I don't know why it happened. I'm sorry. Where is the slide? Yeah, here it is. I'll share the screen. So I'm audible right now, right? Okay.
Yes, sir. Now, sir, you are audible.
Yeah, okay, thanks. Okay, so we just don't have decoherence or the T1 and T2 kind of noise characteristics. We also have gate characters. So what I was trying to say was that the reason we can't break RSA is not just because of the limitation on number of qubits that you would have heard, but also because of the noise. So there are three kinds of noises which are usually there in our circuits. First is this T1, like the noise which is characterized by T1 time. So basically what it means is that if a state is at it's a higher state, at an excited state, it can collapse or go down to the ground state or the de-excited state. So so that is not something we want our state to be in. So if you want our state to be qubit 1, if it is 0, then it defeats the purpose. Then there is another kind of characteristic, that is dephasing time. So what it means is that if you're having a state and it is represented in terms of a matrix, so off-diagonal elements of the matrix, they tell that there is a transition probability. So in dephasing, what happens is that those off-diagonal terms go to 0. If that happens, that means that the superposition character is lost. The transition probability is not there, right? So because of that, if that happens, the dephasing happens, then the quantum advantage is not there anymore. And there are gate errors. So suppose I want to rotate my state from with respect to some axis by pi by 2 radian, right? 90 degrees. If instead of 90 degrees, it happens to rotate it by only 87 or 95 or some other arbitrary angle, then that also defeats the purpose. So all these three attributes lead to noise, and that also functions as bottlenecks. So this is the way we depict. This is called Bloch sphere on the right hand side bottom of your screen. So this Bloch sphere tells you that so the above state that you see is 0, and the down let's say the north pole and the south pole. North pole is get 0, south pole is get 1. So and the surface of the state is where all the pure states live in, which we actually write in terms of superposition. Alpha 0 plus beta 1 is actually living on the surface of this Bloch sphere. So what noise does is that it reduces the magnitude so that the tip of the arrow is not touching the surface anymore. Now it is inside the volume of the Bloch sphere, and it signifies a particular what we call a mixed state, right? So there is some noise is being a part of that particular state. And then dephasing, what it does is dephasing shrinks it, and the decay. So what it does is it just rotates this particular state from the location that we want it to be. So this is the way we geometrically depict what noise does to our architecture. The model exponential bottleneck. So this function requires thousands of entangling gates in a sequence. For its time, T1, qubits lose their state memory in microseconds. T2, that is the gate time. Each operation takes nanoseconds, and during that time, if the decoherence happens, then it's gone, right? So the advantage is gone. So the race is we must finish the calculation before the qubit forgets the data. So we do hard work, we raise our qubit to particular level, and we have to finish off with all the operations till the qubit decoher and forgets the data. So this is the particular race that we are at. So current reality is a circuit for n equals to 2048 is too long. The information decays into random noise long before the answer is found. So how that happens? The gate fidelity that we require, which is practical, is like what we have today is single logic gate error is around 0.1%, which is a better case, so sort of the best case as of now. But shorts require actually billions of gates. For 2048 encryption breaking or decryption, we need millions of gates. And if that happens, it's 0.999. If you multiply that by itself with like a billion times, it essentially goes to 0. So mathematics was the one that helped us, and again, mathematics is the one here that severely limits us. So the solution again is a fault-tolerant quantum computer. So we don't need physical qubits. When you hear that somebody is coming up with a quantum computer and his quantum computer or their quantum computer is having 256 qubits, they're essentially trying to say that we have physical qubits. What we need are logical qubits. Logical qubits are the qubits that are not mired by these errors, these decoherence and gate errors. They are robust against them. So they are called logical qubits. And the problem is, for each such logical qubit, we actually need around 1,000 physical noisy qubits, right? And that's a very big bottleneck. So to scale, to break RSA, we need millions of physical qubits. Today we have only hundreds of physical qubits, and even they are not enough to make even one logical qubit or fault-tolerant one, error-corrected qubit. That is one of the biggest practical roadblock to realizing the advantage of Shor's algorithm. Now there is a decryption. Am I audible?
Yes, sir.
Yes, sir.
Hello? Yes, okay. Somebody was calling from your side, that's what I'm saying. Okay. So the shield is that PQC. So what I mean by that? So RSA is there. Once again, Satish sir is calling. Hello? Yes, sir. Yeah. I just need 5 minutes. I just need 5 minutes more. That's okay. Yeah. Okay. Sure. Yeah. So. Hello.
Yes, sir. Yes.
Okay. So I'm audible, right? Okay. Sorry, maybe the battery down. Okay. So I'll just take a few more minutes, not more than that. So RSA algorithm, RSA encryption is vulnerable by Shor's algorithm, but even though now we are not at the stage at which we can actually challenge or we can decrypt RSA 2048 encryption, but still there are organizations which are saying that we don't have to wait for quantum computers to become efficient enough so that our data becomes vulnerable. So there is a standard, there's a American institute under the Department of Commerce there. It's called NIST, National Institute of Standards and Technology. They come up with certain replacement for RSA encryption. One of the encryption that they rely on is a mathematical problem of basis finding or shortest vector problem finding in a n-dimensional lattice grid. So this is the grid. So we have to find the shortest vector, like from point A to point B, and let's say the basis is not given to you, just arrangement of the grids are given to you. Then first you have to figure out what is the basis, and then you figure out the shortest vector. So this problem is the one which doesn't have sort of the periods that can be found by some uh, mechanisms like quantum Fourier transform. So this works as a shield in the regime of post-quantum cryptography. So NIST standardization came in 2024. They said that we cannot wait for quantum computers to come. We must change our encryption now. So they have decided this Kyber for replacing RSA directly for general encryption. So and dilithium for digital signatures, for Sphinx Plus as a backup hash-based signature. So the mathematics is lattice-based cryptography, it's called. And instead of factoring numbers, these rely on finding points in a higher dimensional grid. Basically, they suggest that the grid should be at least in 500 plus dimensions. It is mathematical attributes, so they don't have to be physically intuitive. So why it works? This problem has no periodicity for the QFT to exploit, and it is the geometrically hard even for quantum computers. So the threat is harvest now and decrypt later. So why there is a rush? Hackers are stealing encrypted data today to store it until they have a quantum computer 10 to 15 years from now to decrypt it. So, so that's why we are in a rush to build quantum computers to like first break the encryption, and then there is a race from the PQC side to shift from RSA encryption to some other Kyber based lattice-based cryptographic encryption so that quantum computers are not able to break them. And now people are even trying to figure out ways and algorithms to even make PQC vulnerable. So there is a race between these two. So because it's an FDP, so there is an action item for the faculty. So you start incorporating PQC algorithms in your cyber defense curriculum, which I think you would already have, but this is a suggestion from my side. So in the theme of cyber defense, we did show that Shor's algorithm works, but still encryption is not gone. PQC is the way forward. So the conclusion, the symphony of interference here. So there is a chaotic wave, and from this wave, QFT or the Shor's algorithm helps us to get one clear spike. But the only bottleneck is that we don't have fault tolerant quantum computing as of yet. So there is one misnomer or misconception about quantum computing. So it's not parallelism that is helping us always. It is always the interference that helps us. So quantum computers try all answers at once. Okay, that's fine. But then they use the QFT to make the wrong answers destructively interfere or cancel out, and the only right answers then emerges out of that QFT, which actually constructively interfere. And those amplify and they actually are the answer that help us to break the encryption. So the role of simulation, which I gave the example of Universe. So we use CDAC's Universe not to break real encryption, but to visualize this interference pattern. So it bridges the gap between abstract linear algebra and physical intuition. So future landscape is the threat on RSA, ECC are mathematically vulnerable to quantum period finding. The defense is PQC, lattice-based cryptography provides a geometric defense. The roadmap is from simulation of today, we make use of noisy hardware, okay, and eventually we go to fault tolerance, and that is the breaking point. The moment we achieve fault tolerance with a few millions of qubits in our hand, that is the point at which we break RSA, right? So as we move forward, the convergence of AI and quantum in cyber defense will be defined by this race. So building better quantum hardware versus deploying better lattice-based software, and these would be in tussle in the coming future. So these are the references for the talk of today. So I thank you very much for your attention, and thanks for inviting me for this talk.
So can you please showcase slide number 21 for a second?
Sorry.
Slide
Hello?
number 21. Slide number 21, sir. 21.
Yes.
Thank you, sir. Thank you very much.
Okay. This is slide you wanted, right?
Yes, sir. Thank you, sir. Got it. Thank you.
Okay. So I'm ready to take any questions. Somebody has, please fire away the questions. I would be willing to answer them. Yeah. Mr. Bakchi wants to ask something. I'm not able to see the questions on screen, so please somebody can say and I will answer.
Am I
Next
audible?
slide, please. 22.
Yes,
Next
yes.
slide.
Yeah, this is the
Yeah,
next slide.
am I audible?
Yes,
This
you're
is
audible. Yes, you're audible. Please ask.
Yeah, I wanted to know, how can we access the quantum computing server which is at CDAC Pune? Is it possible through our normal internet connection through our mobile, and we can access and we can get the results? Is there an option?
Okay, so
CDAC
whatever
Pune or
access to quantum computers we have are from Rigetti or IBM as of now. So even they also provide us like a limited amount of run on their cloud like services. So you can directly make avail of that also. And but the thing is that their interface is not as user friendly as our Quniverse platform is. So if you make an account on Quniverse, and then if you make use of your gates and you run that through the super stack that IBM provides, that would be much more helpful to you, sir. So indeed, you can make use of your usual internet connection and all to make use of the facility. Hello? Any further question, please?
Participants, if you have any queries, you can ask us.
Yes. I know it's a bit late, but
It's okay, sir.
yes.
Okay. Can we conclude like you don't have any other queries?
Yeah. In case somebody has some question and they are not willing to ask me now, or they're very tired, they can always connect with me on LinkedIn, or send me their questions on divyansh@cdac.in, my email ID. I request the organizer to provide my email ID to all the participants so that
Sure,
if
sir.
they have the questions, they can send me the questions.
Sir, can we have a classical computer? Can we incorporate this algorithm to the classical computer and implement this?
See, Quniverse is running on classical computers only as of now, right? So the super stack that I showed you was like sending the information in a transpiled way to some quantum computer out there. But what I did not show was we can run these the simulation, or we are indeed running the simulation on our own like Param Utkarsh and all these supercomputers or classical computers. So even on your laptop, your computer, you can make use of the memory over there, the RAM over there, to perform matrix multiplications, right? So this quantum gate operations are nothing but matrix multiplications. So that you can do classically also. The only problem is that you will not be able to do those matrix multiplications for very big matrices. So if you have a n qubit system, n qubit state, and if you want to apply a n qubit gate on that, so that would be 2 to the power n times 2 to the power n dimensional gate. Now, if n goes above 40 or 50, essentially your classic computer will not be able to do with that. Right? And here for RSA, we are talking in terms of millions of qubits requirement. So imagine the complexity of the gates that are required. And there comes the bottleneck of classical computers where they fail to perform, right? That's why we need quantum hardware to actually perform all these calculations, because there, on the hindsight, matrix multiplications are happening in our understanding, but they actually don't have to go through all the calculation. It's like your brain, coming up with some intuition, and you're not able to recollect from where the intuition came in, but they are a series of operations that are biologically happening in your body, right? We can write the mathematics behind it, but doing that, solving that on piece of paper or computer would be way harder than what the biological systems actually are smart enough to do. They skip through the arithmetic. Yeah, I think
Yeah.
I made this point clear.
Yeah, thank you, sir.
Okay, okay. Any further question, please?
Okay. I don't think
Yes.
there is no questions yet.
Okay, okay.
Okay.
Indeed, if
Thank-
there are questions, you can please connect me or send me on my email ID. I would take
sir.
up the question and answer. Yeah.
Sure, sir.
Okay. So I thank you once again for giving me this wonderful opportunity for connecting with this FDP program. I hope I was able to convey what I wanted to convey in a meaningful way. I tried to skip through a lot of mathematics here, because that would have made it more complicated, and it would have taken more time. Actually, QFT, QP, these topics themselves are semester based topics. Like, people can go on and on about these topics. They're so beautiful, mathematically speaking, but because the shortage of time, I have to skip through that. So in case somebody have questions about those topics, they can always reach out to me, and I would be more than willing to answer. So thank you. And I can conclude the talk.
Okay, thank you so much, Divyansh sir, for sparing your time
Yes.
and giving us a more beautiful session. So thank you,
Thank you.
sir. Thank you so much, sir. And
Okay.
thank you, participants. Participants, for your kind information. The feedback link for both the sessions will be posted by 9:30 p.m. and then that will reach you through some means. And I hope everyone have the QR code scanner with you. So that QR code, we are planning to post the feedback link by the means of QR code. So that will be displayed in the screen for the 5 minutes. Once the session is over by 9:30 p.m., you can scan and then you can give your feedback there. So that will be considered as the attendance. Thank you so much. So we are moving on to the next session. Now I call upon Dr. G. Sendil Kumar, Professor, Department of Computer Science Engineering, to give introduction about the case.
Good evening, all. Sir, good evening, Saravanan, sir.
Divyan, sir.
Sir, Saravanan,
Sir,
sir,
your
good
camera is
evening.
on. Still.
Yes, sir. Good
Okay.
evening.
Yeah, yeah.
Okay.
Yes, good evening. Welcome you all. Dr. K. Saravanan, ME PhD, Associate Professor, Department of Computer Science Engineering, Anna University, Chennai. Dr. Saravanan serves as a Deputy Director at Center for University Industry Collaboration, Anna University, and he holds a PhD in Computer Science Engineering and a ME Software Engineering. His research domain include cloud computing, IoT, blockchain, AI, and educational technology. He has 18 years of teaching and industry experience. Dr. Saravanan has guided 32 ME scholars and 9 PhD scholars, which including 2 completed and 7 ongoing. He has published 39 international journal papers, which including 17 international conference papers. He has authorized 29 book chapters and edited 18 international books. He has completed multiple funded research projects, and also he served as a head of the department CSE in Anna University Regional Campus, Tirunelveli. Also received more than 30 lakhs research funds for the various schemes, which including research support scheme of young faculty and the development of a Android application development. And one more is remote centered infrastructure set up from ISTE. And there is from Tamil Nadu Chief Minister research grant, Intelligent Word Recognizer for Ancient Tamil Paleographic Script. So, and he has awarded and honor for various his work, and journal and editor reviewer for the board of various journal, which including Entertainment Computing Journal elsewhere, and Information Processing in Agriculture, and also International Journal of Data Science and Technology. And also SAR is served as a Journal of Network and Computer Application elsewhere reviewer board, and he has acted as a board of studies member for various colleges and universities, which including WorldTech, JPL Institute of Technology, and many more colleges. And he is a fellow of IEI and a senior member of ACM and IST. He has delivered more than 80 guest lecture and coordinated numerous national level workshop. So his experience is well to help you to today's session. I welcome you, sir. Sir, I welcome you, sir. Saravanan,
Yes,
sir.
sir. Yes, sir. Can you hear me?
I hand over the session to Saravanan, sir. Thank you, sir.
Thank you, sir. Thanks for the introductions. I hope the audience will continue. There is a listening because there's a long day, and that's also the raining in there is in Chennai. So my topic would be in quantum computing and applications in different sectors, not only in different sectors, but also the different use cases and different applications that can potentially harvest the influence of there is a quantum computing. Yes, so quantum computing is a revolutionary approach to computation that leverages the principles of quantum, that is a mechanics. So the quantum mechanics, so it was exist, there is a 3 to there is a 4 decades, there is a before, but due to the emergence of all there is a technologies like there is a cloud, the fog, and the edge computing. So the cloud computing is also, it is in matured, there is a stage. There is a countries and also the worldwide, they have come up with there is a quantum mission to identify the quantum sensing as well as the quantum hardware, quantum softwares, and all sort of there is a technology. Just a second, I put a call from the team. Hello. Yes, it seems Clashore mode, I think. Just can you able to see the slides? This I get
Yes,
any?
sir. Yes, sir.
Okay, so can you able to see the
Yes,
slides,
sir.
right?
First slide.
Okay,
Yeah.
yeah, thank you. So, so I think the first, right, there is a speaker itself, there is a spoke about, right, the quantum. So instead of there is a bits, it uses there is a qubits, and based on the number of there is a qubits, the number of there is a states is also getting increased, because if we say there is a 5 is the number of qubits, the number of states would be there is a 2 to the power of 5, which means that the 32 there is a states we can make simultaneously, we can able to there is a perform. So all the there is a processor and the research will be going on to increase the number of there is a qubits, which requires a lot of there is a hardware investment as well. But if there is a predict with the help of right there is hardware evaluations and so right. So definitely we could be able to achieve right with more number of there is a qubits in the there is a near futures, probably in the number 2030 or the 2040, right? We could come up with there is a more qubits or the more there is a quantum hardware, then we could be able to come up with the more there is a quantum sensing and quantum communication and quantum algorithms as well. So this enables the quantum computer to solve certain problems much faster than there is a classical.
Sir, sorry, sir. Slide no presentation mode varla, sir. Slideshow mode. It is in the.
We're still on the first slide.
Yes, sir. Yes, sir. Please refresh it, sir. Sir, disconnect button again. Share it, sir. Now it is working. Yeah.
Now it's working, fine.
Now it is good, sir. Thank you, sir. Now it is.
Okay. So I think you are in right, the same page, right? There is a quantum computing and introduction. There is a slides. Okay. So not all the problems can only be solved by there is a quantum computers, but some are there is a practically unsolvable problem, like all the kind of NP hard there is a problems can able to be solved by there is a quantum there is a computing. So that's why right it is go with more there is exponentially faster than there is a normal computers. So even the world fastest supercomputer would take centuries or millennium. So while the quantum definition there is minutes or hours. So there is a threat. So what happens, right? We could able to break such kind of there is RSA, there is encryption, which may take time, but when you say there is a quantum, there is a possible. So when it is there is a possible, right? The hackers will able to download there is encrypted text and then they could able to harvest there is a later as well. So that's why right we have to identify there is a post quantum, there is a cryptographic techniques or there is a quantum there is algorithms to there is a prevent such kind of there is hacking. So the key principles of there is a quantum computing evolved from right. It's not from the 0 to 1. So but it's both simultaneously to its there is a superpositions. So because of its superpositions, he can hold there is a different there is a states as there is a simultaneously like there is a human. So what a human can able to there is a think they can there is a perceive the things at once, right? So when we, for example, right, you can say some a person when they speak, they can also able to listen. They can also there is a sense lot of things. We have lot of there is a sensor in bit, right? We can able to there is a watch, we can able to hear, right? We can able to there is a sense. So that's the kind of the ability we can example. We can there is portrait to there is quantum there is a computing as well, right? You can able to simultaneously hold all the state and which is the best there is a possible there is a next step it could be, right? There is a prediction can happen with the help of the quantum computing. Another there is a beautiful attribute or the future of there is a quantum computing is entanglement. So which means right the quantum interconnected. So the states of one affects the state of another because we have there is a more particles and each there is a device or there is a quantum there is a device or the quantum particle can able to communicate with another device and can able to relate with another there is a device, which is a very powerful computational capability or a feature that quantum computing can able to offer. So the classical computing is just about 0 or 1, whereas the quantum computing can be both there is a 0 or 1, which is a superpositions, and we can also present the states with n qubits is going to be 2 to the power n states simultaneously. So the classical computer checks one possible answer at a time, whereas a quantum computer checks so many possibilities in at the go. So qubits go with a deterministic logic, whereas a quantum computing, on the other hand, uses a probabilistic logic and quantum gates, allowing it to process vast combinations of data simultaneously. So usually, right, the humans also work on the same way. We think in a probability logic, right? So that, right, which is the best possible answer, which is more accurately, we can say there is 99.9% is the probability loss of work in the more there is accurate way, right? So whatever we think, right, we'll take the multiple there is a states, we'll think in a multiple there is a perception the way, and we will able to there is a take that next there is a step in a probabilistic way. So that's also right aligned with the, there is a quantum, there is a computing as well. So this makes the quantum computing so particularly effect for more optimization algorithms. So mostly this optimization algorithms go with a, there is a probabilistic way, right, which is kind of not a kind of there is an accurate solution, but it's kind of approximate. There is a logical based solutions, but this approximations is very nearer to the there is accurate solution, which is enough, right, for us to go with a kind of there is a solution. So instead of there is a waiting for the accurate solutions, we can go for a so more probabilistic as an approximate there is a solution in hand. So for the kind of simulations as well as for there is a cryptography, right? So the quantum computing will be the most optimistic there is a solution. And superposition and entanglement, the two the futures that the quantum offers. So superposition allows the quantum states to explore the multiple position at once, which means drastically, right, increasing the computational there is a power source. So because it talks about, right, more kind of there is exponential way of there is a thinking. And entanglement to talk about the quantum there is a communication. This is putting in a proper secure communication using quantum key distribution, like there is a QKT. And together, these principles are from the backbone of quantum computing, so enabling the breakthroughs in fields like cryptography or material science, and as well as we call it as an artificial intelligence. Because when the quantum evolves, it can be linked with AI. We can call it as there is a quantum AI, or maybe with the blockchain, we can call it as there is a quantum blockchain. And for all kind of there is a cryptographic or post cryptographic there is a solutions as well. So the quantum computers are not just faster computers, they use a different physics that allows. So explore the many possible that is state at once and filter the high probability answers with the help of this interference. And exploiting the correlation that's a classical systems cannot able to there is imitate, because it uses the principles of there is entanglement. So this is why some problems are not just hard but practically impossible for classical computing, but still it can be able to solved by there is a quantum platforms with the help of the quantum hardware and its proposition of the superposition principles. For example, so we can talk about some of the applications, like there is a drug discovery and molecular there is a simulations. So imagine, right, how much time would able to identify there is a new drugs. So there is a scientific discipline. It takes year to year because of lot of there is a simulation to be there is a perform. So where in case of there is a quantum there is a simulations which takes in more there is exponential there is a fashion. So these modeling and molecular interactions can happen in exponential way, and we could able to deliver this there is a drugs on time. And also all the simulations can be taken in a there is a very faster way, and with the help of the entanglement, with the help of this molecular there is a simulation. This there is a particular there is particles communications in a molecular can happen in a more there is a faster way. So more there is a form of layers will explore these kind of there is some options where Roche, Johnson and Johnson, right? They started taking on this kind of there is a quantum hardware, and they exploring or the possibility of finding the drug discovery using the quantum hardware. Even Pfizer, there is collaborated with IBM to simulate the molecular structures using the quantum there is a computer. So Pfizer is one of the very famous, right? There is pharmaceutical, there is a company which is helped in there is a Corona, right? There is antivirus molecule, right? Also, to step into there is a quantum, there is hardware as well. Able to see this link?
Yes, sir.
Yes, how quantum physics and AI is disrupting the drug discovery and there is a development, right? So you can have the kind of there is a 3D, there is a structures of the molecule, and we could able to identify so how the quantum particles can are able to there is a communicating with each other, right? And there is always the pharmaceutical, there is a companies doing the research in it, and we'll find that there is fruitful, there is a solutions and happens to the quantum. There is a computing, there is a software. So personalized medicines and genomics and healthcare. So it accelerates the genome sequencing and mutations and analysis as well, right? Because there's a human constructed with the help of the genes, right? So the genome sequence and the genome analysis. So which if it takes there is will have very millions of there is a years to be there is a computer. So we have to find out each gene will have the individual there is a characteristic can also be identified. So if you identify the individual, there is a gene, there is a sequencing, we can go with the individualized, there is a treatment recommendations as well. The patients, because of the heritage, right, they'll have a lot of, there is a diseases in hands. So in order to, there is to go for the kind of, there is a treatment. So we have to go with the individualized treatment recommendations as well as the plan. So for which, right, so have to go with huge amounts of there is a genes, there is data for further there is a persons and how we there is a process on how we able to there is a predict these kind of there is a genome there is a sequencing and how the mutations have happened in the there is a genes. So for which right we have to use that there is a quantum there is a case studies and then quantum there is a power. So it's not about only there is a quantum there is a computing, it's also aligned with there is a quantum there is a machine learning because the genes will generate that huge amounts of there is a data and we have to make kind of there is a predictions of from the existing there is a data as well. It will support the precision oncology as well as rare disease diagnosis in place. Still the machine learning algorithm right cannot able to there is a predict such kind of there is a rare there is a diseases. The aligned if it helps with there is a quantum ML right it can able to do it there is a very there is better way. So there are some researches are going on from there is a lot of there is a companies like from IBM as well. So IBM can come up with lot of there is a case studies. So with there is a quantum especially right they have a quantum kit right for example this is also there is available. So for our researchers and they have doing this there is a quantum this case studies in a different there is domains as well. So this is one of the case study for a quantum from IBM Quantum Systems. And for biotechnology disciplines and for molecule right drug discovery and electrical grids and semiconductor industry and Boeing for supply chain management and for this chemical industry and for electrical vehicle in a battery technology. So they have taken the many domains in parallel, right, to harvest whether there is a quantum technology as well. So the human body contains there is a more than lakh types of proteins and each protein is derived from a RNA which is genome. So the scientists have known the mRNA has a potential from the basis of new class of medicines that could address the illnesses of the most fundamental levels of the cellular there is a functions. So for which right we could elevate right with the help of alleviate the diseases with the help of the IBM there is a quantum solutions. So it enables a complex biomarker. There is a pattern discovery using the quantum alcohol. So because I have to identify that there is a pattern of this genome, there is a sequences, right? Genome sequencing with the help of the quantum ML algorithms. And another, there is a solutions is for there is a traffic, there is a flow optimization. So Volkswagen, they already there is a started using there is a quantum based route optimization systems in Lisbon and used D-wave quantum annealer to reduce the congestions by dynamic route optimization. Because of dynamic route optimization, right, is still a kind of very big. There is a problem with the help of there is a number of there is a vehicle number of pedestrians, right? Some V2X networks, vehicle to everything. This is also there is emerging, right? So when the people start using, there is a more V2X, there is a networks, and we have to go with a more dynamic route optimizations as well. So it's a kind of optimization, and with the help of there is a real data, and it should happens in very real time as well. So such kind of there is a complex problem that should be solved in a very real time manner, right? So again, so the quantum computing will be the most optimal. There is a solution for this case. So Volkswagen optimizes the traffic flow with the help of the quantum. There is a computing in a particular Lisbon, there is a states. So which means there is a lot of industries will using the quantum, right? There is a computing, right? For this optimization, there is a problem, and for their bus fleets, right? There is various, there is a use cases, there is a come up with the help of the quantum, there is a computing as well. Here I can say there is Volkswagen uses the quantum computing to tackle pervasive global problem like smart traffic management is an example of the real world impact quantum complications we soon have our cities, communities, and everyday lives. So since we built the first commercial, there is a quantum computer, which is called the D-Wave from Volkswagen, has been focused on designing the system that enable the quantum application development and deliver there is a business, there is a value. So they have ITS, intelligent, there is a traffic optimization, there is a solution with the help of there is a D-Wave. The quantum based there is a solutions which will give the better optimization as well as the better there is a prediction of the ongoing there is a traffic flow in the there is a city. So it's a kind of there is a pilot, there is a project which involves a quantum, there is a hardware as well as the real time there is a data, there is a link. Though they have taken the 26 stops where there is a selected and connected to form the 4 there is a bus links with the help of the quantum route optimization algorithms. So portfolio optimization, risk analysis. So especially go with the rate that is a finance. So quantum optimization algorithm improves asset allocations and hedging because we have lot of this asset managers who have whose this function is to allocate the there is a shares given by there is investors. So a lot of there is a people start investing in right. There is a share right. So the exact that is asset allocation should be there is a done by this asset managers and so on. Right. So how we can there is a do it and how accurately we have to do it because these shares happens in a there is a very real time. Hello. Get some sort of ego. Hello.
Dr. Anita, madam, please mute your. Dr. Anita. Dr. Anita, mute your.
Hello. Yes. So consider the case of right lot of there is a people investing in there is a stock market right. So the asset manager has to do the asset allocations in a real time, and of course we know that right. So the portfolio on the shares we are the highly there is a volatile there is a market. So even it goes with for example the crypto right. There is a bitcoins and there is cryptocurrencies as well. So these are all very high volatile there is a markets. And you highly dependent on this kind of there is asset, there is a managers and so on. So how we have to more optimally allocating these assets in a particular there is a share. So we could use there is a quantum, there is a computing. We'll take more approximations because again, if we say there is a share, it's a kind of we can't again go with the more accurate solutions. It's all going to be more approximations only. So these approximation and the optimized there is a predictions, right? As asset allocations can happen with the help of there is a quantum algorithms. So faster Monte Carlo simulations for risk estimations and enhanced fraud detections using quantum ML classifications. So already Goldman Sachs, so and also the JB Morgan. So already there is a starter. They are very big. There is a financial, there is a companies and financial, that is prediction companies started using the IBM and QZ. There is a partner. They partnered with IBM, right, for the quantum. There is a computing ability, and they already started using there is a quantum, there is a processing ability. So JP Morgan uses the quantum approximate optimization algorithms to optimize the investment, there is a portfolio system, and achieved the better simulations of risk return trade-offs under there is uncertain, there is a market. Because since it is a high volatile, there is a market. So you have to reduce the the risk, there is a factors of the investors, which can be done with the help of there is a quantum, there is a computing. And next goes with the cryptography as well as the cipher security. So Shor's algorithms can break the RSA and the ECC encryptions maybe in a near future. It may happen by 2030 or so. So how we have to, there is a tackle there. So that's why we have to come up with, right, not about the quantum cryptography, it's about the post quantum cryptography. So if there is a threat happens, how we have to tackle that. So for this, right, you have to evolve with more algorithms like with the post quantum cryptographic algorithms. So more researchers there is going on the cipher security arena, and we need, right, there is some more post quantum cryptographic algorithms as well, right, for to relook at our security. There is a redesigns, because if you go with the security zone, there is a threat, we have to redesign the entire, there is public key, there is a cryptographic algorithms as well. So IT Quantic deployed a quantum random generators for secure encryption algorithms as well as for quantum cryptographic distributions as well. So used in Swiss banks and telecom networks to protect the sensitivity to the transactions. So applications in banking, defense, and secure communications already started using there is cryptographic methods using the quantum computing. So next go with the logistic and supply chain optimizations in industries and commerce. So it solves the vehicle routing. So logistics will have a very big supply chain. There is a management, and we have more right. There is issues as well because of the entire there is a supply chain management. There are more computations involved, and there are more algorithms to be effective SCM supply chain management. So real-time dynamic route planning for fleets, drones, and warehousing, and cuts the delivery costs and energy and carbon emissions can happen with the help of the quantum computing. So DHL uses the D-Waves quantum annealers to optimize the deliver truck routing. So focus on reducing the ideal times of fuel costs and improve the delivery efficiency as well. So we can cut the fuel costs and also we can improve the delivery efficiency as well. So climate modeling and weather forecasting with the help of the Earth and climate sense. So quantum simulations with the better there is simulations of atmospheric and ocean dynamics, because of there is a climate modeling, since it's a very huge, there is a challenge for us, right? So the extreme, there is even prediction will happen. Even, right, we can say that, right? So now in there is a channel, the Tidwar, right? There is prediction happens, but still again, so the predictions go with there is a very wrong, because we cannot able to there is a predict that there is a futures. It may change even within there is hour or there is a minutes, but how we could able to there is accurately predict the kind of there is a cyclones even that, right? So we have such kind of that is prediction with the help of there's a quantum annealing, right? So go with the not with there are more attributes and more there is a quantum machine learning will happen. So the predictions rate and the approximations will also be there is a more accurate then. So more accurate climate change policy, there is a forecasting can happen with the help of there is a quantum computing. It improves its accuracy, it improves its optimization, and improves its approximations as well. And NASA and Google Quantum AI uses the quantum processors to improve the model accuracy in whether there is a predictions. So already there is a research is going on, right, from the Google as well as the NASA, right, go with, right. So more there is quantum based, there is a satellites, and more quantum there is a sensors, and quantum more quantum there is a radars in place. And quantum machines learning algorithms are trying to detect the anomaly patterns in satellite. There is a data as well. So we could able to identify these anomaly patterns in satellite data. So which could able to there is a predict the climate modeling in, and also more the climate there is a designs as well. And next goes with the smart grid optimization and energy there is a systems. So quantum algorithms can help balance the power supply demand with renewables. So how much there is renewable, there is energy in hand, and how much we have to there is a produce, right? So all this have to be done then in there is a parallel, right, with the help of there is a quantum computing. So grid fault reductions and power flow optimizations can be done with the help of the quantum computing. So optimize the hydrogen storage and fusion material simulations and used in smart cities and national energy. There is a plan. So fraud detections and threat intelligence. So financial and enterprise, there is a security. So quantum machine learning, along with there is a machine learning, the concepts can able to detect some rare anomalies. There is a patterns. So these anomalies, there is a patterns can able to there is a detected. And so with the help of there is a quantum machine learning algorithms and faster classifications, because the quantum there is a states can able to there is remember can be able to grow exponentially, right? It can able to do the classifications in a very faster manner in an exponential way. So can able to classify the such ways there is a transactions and hardens enterprise and SOC as well as the AML there is systems as well. It can be used by there is a banks. So now also there is a bank used to identify the suspicious there is a calls, but with the help of this, right, there is a quantum. It can be able to done in more there is exponential there is a faster way. So used by there is a banks and insurance as well as the payment there's a networks as well. So AI accelerations and optimizations in different there is a cross industries can be able to there is a benefit with the help of this quantum there is a computing. So quantum speed up for optimizations, heavy ML workloads, and faster training and inference for large AI there is a models. So it improves the recommendation systems on larger scales NLP. So can work with there is natural language processing applications as well, because since it's a quantum, right? So it's a quantum computing. So the quantum computing can be coupled, right? Can be aligned with a lot of other there is a technologies as well. It can be used with the hardware. It can be used with the sensor, which means we go with it more VLSI based applications can also be developed. It can be go with artificial intelligence applications like machine learning as well as for natural language processing NLP based applications as well. And hybrid quantum AI pipelines are under development. So which means, right, so quantum harness with AI, there is a technology. So we have to come up with there is a more solutions then. So already we are talking about this generative AI and agentic AI. So the quantum can able to couple with these kind of technologies as well. And materials discovery. So not only, right, you can go with there's a molecular this molecular and drug discovery. So new material science, right, materials engineering can also be benefited with the help of there is quantum, there is a computing as well. So simulates a new alloys and superconductors and photovoltaics. So we have to design the new alloys and the new materials with the help of there is a quantum computing as well. So improves the battery, there is materials, electric vehicles and energy, right? So if you go with there is electric, there is a vehicles. So the quantum computing can also be used in potentially identifying the electric vehicles and the new moleculars there is designs as well. And lightweight and high strength aviation materials discovery can be done with the help of there is a quantum computing and used by Airbus, Toyota and Boeing. The research team are doing right more kind of new alloy designs and superconductors and photovoltaic designs with the help of right quantum there is a computing. So this is a kind of this application. There is a summary, right? Excluding this the defense, which we are going to. There is a say. There is a later. So in healthcare, transportations, so finance, logistics, energy, so climate, cyber security, fintech, agriculture, smart energy, right? So there are a lot of there's organizations also using Pfizer, IBM, so Volkswagen, JP Morgan, DHL, for example, for logistics. So all the major players, if you take any major players, so they start cultivating the quantum technologies and they start investing huge amount in a quantum hardware and quantum sensing for developing the quantum. There is a solutions for there is a problems. So ID Quantic and there is a MasterCard, BASF, Siemens, Atas, right? So all these companies start investing in there is a quantum, there is a solutions. So role of there is a quantum computing in defense applications. So cipher security and cryptography used in quantum computing can break the current encryption standards, making post-quantum cryptography, making it more essential. And intelligence and surveillance enables advanced signals intelligence by processing vast amounts of data in real time. And military hardware, quantum materials enhance stealth detections, autonomous weapons, and precision navigations. So what is maybe that's a stealth detections? For example, right? So we know about there is a lot of there is a drones, right? In used in there is a wars. Even in the India, there is Pakistan, there is a war, right? So a lot of there is a drones are used instead of right other there is a weapons. So these steals can be identified with the help of there is a quantum radars, but there are some stealth there is drones which can be right used in the there is a used in the there is a war concept which can escape the quantum radar. So if you have to identify those kind of there is a stealth detections, you have to use such kind of there is a quantum radar instead of there is a classical radar. So the classical radar failed to detect these kind of there is a stealth drones and then stealth there is a machines, whereas the quantum radar can able to identify these there is a stealth radars as well. So quantum materials enhances these stealth detections and autonomous weapons and precision navigations and defense logistic optimizations. Quantum AI improves the battlefield resource allocation and strategic sensing with the help of there is a quantum sensing, because because all these peoples who have to go with more dynamic resource allocations, we don't have what is the resource in hand, because we lost a lot of there is a resources, lot of there is a weapons, lot of there is a people in a real time there is a war. So you have to allocate the resources currently in hand in a battlefield. So the quantum machine learning algorithms will help you to identify what is the exact resource can be allocated with the help of there is quantum computing. And economic warfare, there is a protections. It secures the financial markets and critical infrastructures, and there is a government, there is a data as well. So this is there is a big picture of there is a quantum warfare. You can see that. So what are the way it can able to there is a communicates, which means it's not only there is undergrounds, there are some underwater, there is a mapping as well. So quantum underwater, there is a warfare which will be used in quantum. There is a marine systems. So both will be in right military as well as air force as well as in navy applications. So quantum computing can be used. So quantum underwater, there is a warfare which can be used in underwater. There is marine, there is systems which can able to detect which are the marine, under marine objects are there and can able to detect and then be able to avoid in those machines. And quantum underground mapping. So we can able to detect these kind of there is an objects in the underground. There is a mapping with the help of there is a quantum radar and quantum lidar applications. And quantum inertial there is a navigations, and with the help of this quantum communication in satellites, even the GPS there is a fails in a real time. Still, you can able to tackle with the help of this quantum. There is a radar quantum radar applications. and quantum computing applications and quantum, there is a warfare, right? As a kind of, there is a holistic applications which can help this quantum underwater and quantum inertia applications. So the entire, there is a quantum technologies, quantum in defense, which can be used. So quantum radar is an advanced remote sensing technology that uses the quantum mechanics, such as the quantum entanglement, to detect the objects more effectively than conventional radar. It excels at finding the stealth aircraft, as I said right previously, and also the missiles and submarines by analyzing the correlations between the entangled photons, allowing it to detect the faint signals hidden in a noisy environments. We'll see one of the video here. So that's why, right, the quantum radars and then quantum radars will make a very great impact. So in the evaluations of identifying the stealth, there is an aircraft as well as the missiles, as well as the submarines. In a there is a real-time manner. And role of quantum technology in defense. So cipher security and cryptography, it uses quantum computers to break current encryptions, so leading to the development of post-quantum cryptography and quantum key distributions for secure communications, and used for intelligence, surveillance, and reconnaissance. So quantum computing can enable advanced signals intelligence by processing vast amounts of data in a real-time manner. So which means the quantum sensor can also be detect the minute changes in the environments, because the quantum sensor, the sensitivity is very, very high when compared to the classical, there is a sensors. When the sensitivity is very, very high, right, which can able to accurately identify even the small change in that there is a particles. So which means, right, we could be able to identify whatever the threats in under there is marine, or maybe the underwater, or maybe the under, right, there is a land as well. So all kind of there is can able to, there is a changes we can able to, there is predict, right, in maybe in there is a military applications and navy as well as in air force applications as well. So it is helping to locate the hidden tunnels or maybe the submarines which cannot be able to identified by that is the normal smart sensors, as well as for logistics and operations in a military applications. These quantum algorithms can optimize so complex logistical problem such as resource allocations, route planning, and supply chain management, leading to more efficient operations. Decision making. So the ability to perform rapid simulations and data analysis can provide a commanders with the timely and accurate information. So because the decision making right for the commanders in a real time, there is a warfare is very there is a crucial, because they should not wait for the commands or for the instruction from others. They have to take the decision immediately because it's a warfare, right? So for which, right, with the help of the current resource allocations, with the current there is a situations, right? So this quantum there is a computing technologies, because they have the multiple there is a states in hand, will have the more accurate and possible optimized there is a solutions to the there is a commanders to make a accurate there is a decisions. And when it comes to there is a military hardware implementations also for radars and there is radars and military equipments. So quantum materials will enhance the steel reductions and improve the performance of autonomous weapon systems. So the weapon systems will become there is a more autonomous in hand now, right? So more autonomous drones, more autonomous radar there is a systems which can be done. It's not about the war will be happen through only the soldiers. So more of the war will happens in futures will happen. There is more autonomous. There is a vehicles only. So that's why, right, we have more kind of there is a drones in replace of there is a soldiers. So if you have this kind of there is more autonomous there is a weapon systems. These autonomous there is weapon systems has to decide on their own or has to more optimized in a there is a real time manner. So that can happens with the help of there is a quantum technology only. And I want to write through some ideas with the help of right there is a quantum nation missions of our India from there is a government of India. So national, there is a quantum mission. This is a very big, there is a projects. So there is fountain in a quantum computing. It's there is a 4 different areas, quantum communications and quantum sensing and quantum materials, which talks about the quantum hardware itself. So quantum materials in the material science and the quantum sensing, and with the help of new sensing devices with more accurate, there is a sensing in VLSI and other domains areas, and quantum communication with the help of more communication between the devices, and quantum computing, which is more kind of quantum AI algorithms, quantum blockchain, and more quantum algorithms in place. So these 4 thematic hubs, which is done by in a different, there is a places from Bangalore IISc, and then from IIT Bombay and IIT Delhi, and from there are different there is hubs. They are doing lot of there is a research in that area, and more there are more proposals right in this domains as well. Go with right the foundations of QC innovations from IISc, there is a Bangalore. So they support lot of there is a startup companies who are doing the quantum there is a research. So not only from entrepreneurship developments, they also with industry engagements, human resource development. They offer the internship to the students as well as for the research. They also offer the postdoctoral fellowships in there is a quantum, there is a computing. So Google, so they have their own toolkit called there is a QSIMS, which is a more optimized quantum circuit. There is a simulation tool. So which is there is a freely available to do the simulation environment. And IBM, which is a Qiskit, is a very famous simulation environment. Initially, there is a start with. So they have 30 million Qiskit downloads, and there are many applications which are already in hand, right? In if you go with it, GitHub or something, right? So you'll have a lot of research, lot of there is a products and lot of there is a simulation tools. They are a pioneer in there is a quantum. There is a research toolkits already. So for IBM Quantum, there is a platform which give more optimization, research ideas with the CUDA, HPC performance systems, Hamiltonian simulations, and machine learning courses as well. I can add, and you could also access IBM quantum computing, maybe in a very limited level. And also, right, if you go this URL, right, you could be able to find a lot of there is a research projects as a simulation level that people have done. There is a lot of there is a research, there is a quantum computing, and there are more research should be done for there is a quantum computing, not only for there is a defense based applications and also for a lot of other domains as well. If you can take it for any, there is a domain which is more computationally, right, very complex, then there is a quantum will be the ultimate, there is a solution, right? And it has very lot of there is a potential and opportunities for the researchers or as well as for the startup companies, as well as for the there is a students to take up as there is a project. That's it from my presentations, and you can have any queries you can ask.
Participants, if you have any queries, you can ask. Participants.
Sir, is there any course available in the IBM QSkit platform, sir?
Yes, ma'am. Yes, I can. I think right. You can see here, right? So they are the pioneer. So they have a lot of there is a tools, and also they are out for the courses as well from the IBM. IBM offers the courses. See here. Can see there is quantum.cloud.ibm.com. For each of the topic, they have different courses, tutorials. Yes. Not only free credits program. So these are the avenue, right? You can check about, right? Who should apply? So there are IBM Quantum Credits program. If you have this eligibility criteria, right, you can able to access the IBM quantum computers as well. This maybe as initial of the plan, we could be able to experiment. Yes. Any other questions?
Any other questions, participants? Do you have any other questions?
Sir, good evening. I'm Dr. Sandhya. You have just shown a few projects that have been like DST and all on quantum, but they're taking very long time in scrutinizing or giving up any decision, sir. Any idea on that, sir?
No, you're talking about the submitting the research project, right? So I'm just giving the venue, right? Where you can able to, there is a LAN and then you can able to, there is identify, there is a problem. So there are a lot of, there is a research and there are a lot of, there is a problem statement as well, right? There is a quantum research is still right in the, there is infancy, there is a stage as well, right? So for us, there are more opportunities, right? It's not about only kind of the research entrepreneur, right? And you can, right? For example, encourage your students to do such kind of, there is a simulation in Roma. So definitely, right, if you apply along with, because the even the IBM, there is a quantum mission encourages the research, there is a proposal that could be submitted. There is a 4 hubs, right? There are 4 hubs under IBM, Indian, there is a quantum mission, right, in which you can able to approach any one of the, there is a quantum mission, there is hub, right? So definitely you can able to, there is connect with them and you can use their infrastructure and you can go with it. There is a particular, there is a problem statement. For example, if you want to go for a particular, there is a drug discovery, right? So you can get the suggestions, you can get the platforms, infrastructure, right, to develop your, there is a solution for the particular, there is a problem statement.
Okay, sir. Thank you.
Thank you.
Any other doubts you have? Any other queries, participants? If you have, you can ask. Okay, I hope there is no question. Now I would like to call Dr. G. Senthil Kumar, Professor, Department of Computer Science, to have a closing note.
Good evening, sir, and good evening all. Thanks to Dr. Saravanan, sir. It's a given introduction to quantum computing and the applications of quantum computing in defense. So he has given various examples from biotechnology and defense and then the traffic analysis. So all these applications are very useful, and also start showing about what are the projects available from various government sectors. So thank you, sir. So this session will be very, very useful for us. Thank you, sir. Thank you.
Thank you, Saravanan, sir. Thank you, Saravanan, sir.
Thank you, Saravanan, sir. Thank you.
Thank you.
Thank you all.
Thank you, sir. Thank you very much.
Thank you so much. Thank you so much, sir. Thank you, participants, for joining the today's session. We will meet again tomorrow at 6 p.m. for more vibrant session from industrial experts and the experts from Malaysia. Once again, I thank all the dignitaries and the participants, and I wish each and every one of you to produce a productive, insightful, and enrichment learning experience in the days ahead. So attendance is automatically generated in MS Team. So additionally, kindly fill the Google Sheet now I'll be sharing. So as per the norms, only participants with 80% of attendance and 70% of the 70% of the marks will be eligible for certificate. So kindly mark your attendance now, which I'll be posting it now as a QR code. Please, just a minute, I'm sharing now. So can you see the QR code now? Participants, can you see the QR code?
Yes, yes,
Yes, sir, we can.
it is visible.
Okay,
Yes, sir.
okay.
Yes,
Please fill this Google form where it has got basic information and asking for the feedback about the session. And 4 questions which you need to answer. So it will be open. It is open now.
Good evening, sir. Sir, how do I go
Yes.
about with the QR code, sir? What do we do generally for it?
Just scan it, ma'am. Just scan it. You have a scanner in your mobile, and if you don't find scanner in your mobile, just open your Google Pay. Right? In Google Pay, you have a scanner. Google Pay. Suppose if you don't find scanner in your mobile, just go to Google Pay and open scanner in that. So you can
Okay.
just scan this, and then that will redirect you a link, which is a Google form, which we have created, and from that you can fill the form and then you can submit.
Let me try, sir.
How
Just
to do?
yeah, I'm
Once
not able
again,
to.
please.
Ma'am, if you don't have scanner, and if you can't find scanner in your mobile, what you need to
Okay.
do is just
Sir,
go
they
to
can
Google.
scan using the camera also.
Yes,
Using
yes,
the
you can.
camera.
Yes.
Okay, I'm just opening it with my.
You better you just you go with your because different camera has got different functionality, ma'am. Don't go with that.
Actually,
Just
I'm viewing this in my laptop, and I'm not able to go parallelly to the other this one.
no, you don't want to go with the laptop. You can go with the mobile phone, right?
Yeah, I can open in my mobile. Is it?
Okay, or else you take screenshot of it, ma'am. I have a screenshot of it. Later you can also do it. Screenshot of it, and then just go to your Google Pay.
Okay.
Google Pay, you have an option like scan any QR code. Okay, you have an option like scanning any QR code. Just go to that and then scan this screen, and then that will redirect to a link. Okay. So if that is not there, if you had this as a screenshot, you can take it from the library, upload from library. So if you click that, can be uploaded from the library.
Yeah, got it, sir. Thank you so much.
Thank you, ma'am. Thank you. I hope everyone did the scanning. Participants, everyone did the scanning, right?
Yes, sir. We have scanned, sir. May I ask a question, sir?
Yes, sir.
Sir, actually, it is just showing some questions also, sir. So, do we have to do it right now or after? See, generally, what
Sir,
happens?
but
It is on the
sir,
last
sir,
day.
yes, sir. Sir, can't understand, sir.
Sir, I'm saying
Hmm.
this link is also having some set of questions, right?
No, only 4 questions are there. They're very simple as well. It's very simple
No,
question.
Yeah,
okay,
4 questions are there,
4
sir.
questions.
yeah, okay, all right. But again, we have to give the exam on day 6, na?
Yes, sir. Yes, sir. Yes.
Okay, fine.
It's very simple question, sir. It's very simple question of today's session. Just
No,
2
I am
questions.
not asking that. I am asking the
Yeah.
final exam will also be there now on the last day.
Yeah,
That's
yeah.
why I am just confirming.
Yeah, we have, sir. We have in that as well.
Sir,
Okay.
after filling the form, can we leave?
Yes, you can leave, ma'am. Once the form is filled, you can leave, ma'am.
Okay, thank you.
Participants, once you are done with filling the form, you can leave. Thank you. Thank you so much for being attentive in the class.
Yes, can GM.
Sir, did everyone join? Sorry, everyone scanned the form. Shall we leave?
No, sir.
Yes, sir. Yes, sir. Done.
Okay, please scan it, ma'am.
Sir, how to scan, sir?
Sir, how?
Sir,
Sir, how to scan, sir?
so do you have scanner in your mobile, sir?
Yes, sir.
Just open the scanner, sir.
Sir. Sir, PDF scanner?
Yes.
Sir, PDF scanner or normal scanner, sir?
Normal scanner, sir. Normal scanner.
I just open, sir.
Yes, open it and scan this, sir. Scan this QR code. Scanned, sir.
Sir, no, sir. Sir, QR code not available, sir.
Sir, do you have Google Pay with you?
Yes, sir.
Open the Google Pay, sir.
Yes, sir. I opened.
Open the Google Pay and open the scanner, sir. You have scanner there?
1 second, sir. 1 second. Scan any QR code, sir.
Yes, sir. You scan that. That will lead you to a link. Fill that link. Can you, sir?
Sir.
Excuse me, sir. Excuse me, sir. Am I
Yes,
audible?
ma'am. Yes, ma'am.
So kindly ask them just to open the camera and then there will be a link. So they need not to do